Okay, so thank you very much. Thanks to the organisers, including Simon, who for putting together this workshop, which is very nice.
Sent his apologies. He would be here
And so, yeah, I mean, in the past, I've done quite a lot of work on matrix models and emergence, space-time, and so on, but I have to say I haven't worked directly on it for a few years now, and so rather than, well, so if I'm going to tell you something, it's not going to be on that. So I'm going to tell you about what I have been doing recently, which is thinking about gravity with boundaries. And I hope that this is a general enough question that it's of interest to people, certainly thinking about holography. I think it's quite an interesting question, just as it stands on its own. So I hope there'll be some useful stuff in here, even if it's not on matrix models or emergence of space-time. In some sense, it's a much more basic question. And this is work done with Xiaoyi Liu, who's a PhD student in Santa Barbara with Don Merle, but is now in Chicago. The last paper was also with Harvey Real in Cambridge, and both of these were with George Santos in Cambridge. So the plan for the talk is I'm going to tell you, or give you a little bit of motivation for why we might want to think about space-times with boundaries. Then I'm going to tell you what happens in the Riemannian problem, or the Euclidean problem. And by that, I mean pure spatial geometry, where you might want to impose something like the Einstein condition, but in the Riemannian context. So Ricci flatness or Einstein metrics. For example, you might be interested in compactifications in string theory that have boundaries in the internal space, and that would then become a Riemannian problem. Alternatively, you might be interested in Euclidean continuations of black hole physics, where we often use Euclidean techniques. And in that setting, a rather surprising, old or recent, depending on your sort of perspective, maybe 20, nearly 30 years ago, it was shown that Dirichlet boundary conditions for that Riemannian problem are ill-posed. And by Dirichlet boundary conditions, what I mean is the analog of Dirichlet boundary conditions for gravity, which is to fix the induced metric on the boundary of the spacetime. Okay. And that is a very surprising result, I think.
What does ill-posed mean?
And I'll tell you all about what ill-posed means, but excellent question. Ill-posed basically means as a PDE problem, you shouldn't impose those boundary conditions. It will not give you a good behavior. So I'll define what well-posedness is, but roughly speaking, it means there isn't a good map between boundary metrics that you would try and prescribe and solutions. So you may be able to write down analytic solutions that solve the boundary conditions, solve the bulk equations, but for example, if you wanted to solve this system on a computer, you would run into problems.
You mean more than just the development of singularities?
Oh yes, much more. No. Yes, it's nothing to do with singularities. This is really to do with, if I prescribe boundary data, is there a good map from my boundary data to solutions? So I'll in a couple of slides, I'll come on to the definition. So that was a surprising result, and actually sort of got buried in the literature. It was originally some physicists who came up with this. Then mathematician Anderson has done a lot of work on this, and it sort of lived in the geometry community for a while. And it was sort of popularized by, obviously, when Witten wrote a review article in 2018. So a small number of people were aware of this, but then lots more people became aware of this in 2018. Now, there's another rather natural set of boundary conditions that aren't Dirichlet, that Anderson wrote down, the mathematician, in this Riemannian setting called conformal, well, I will call them conformal boundary conditions, or Anderson's boundary conditions. I'll tell you what they are, but they're a sort of modification of Dirichlet boundary conditions, which are quite natural for gravity, and they are well posed. And recently we've generalized them. There's a very natural generalization for reasons I don't really understand, people haven't considered, but I'll talk about those. So in the Riemannian problem, it's a bit surprising that Dirichlet conditions aren't well posed, but there are some other conditions which do seem to work. So then you might come to the Lorentzian problem, And the Lorentzian problem is quite a lot more complicated. The analysis of well-posedness is much more complicated. Dirichlet boundary conditions in the Lorentzian problem are probably ill-posed. And I say probably for reasons I'll describe more later. We could say that, yeah. So let me just say, let's just forget the word probably, let's just say ill-posed. We'll come on to it. So you might then think, okay, and essentially for the similar reasons that the Euclidean problem, boundary conditions are ill-posed. And so you might then naturally think, well, what about these other boundary conditions? And they were, in March, Anderson and another mathematician, Anne, published a paper saying that they were well-posed, a long paper proving well-posedness for the Lorentzian problem. And more recently, we put out a paper giving a counterexample to well-posedness. So I'll discuss all of that.
But in the Lorentzian case, you have different possibilities. I mean, as an initial value problem.
So I'll be more clear about what I mean by boundary conditions, because indeed you have an initial. This is what's called an initial boundary value problem. So you have a Cauchy initial surface and then some timeline boundary as well. That's right. And so these boundary conditions are being placed on that timeline boundary. So yeah. But the upshot, the takeaway message for this is that how you have boundaries in gravity is rather complicated and not very well understood at all. Okay. And it's not even clear that in the Lorentzian case, there are any reasonable, there's one type of boundary condition which is sort of very restrictive, which is, so I was talking with June about this yesterday. If you put a brane, the natural boundary condition for a brane, which is basically a condition on the extrinsic curvature being proportional to the induced metric, that is okay. But apart from that, it's unclear anything else is okay. And that's a little odd. So Neumann is essentially that brane case. Yeah, that's exactly it. But normally with Neumann, with a Neumann boundary condition, you want to say that the normal derivative is given by some function, and that hasn't been shown. It's just that you could set the normal derivative essentially to 0 or to some basically proportional to the induced metric, but you can't set it to be some arbitrary.
But that sounds more like Robin boundary conditions, where a derivative is equal to the function.
Yeah, but even with Robin, I mean, you would generalize Robin to say a combination of the function and the normal derivative is equal to some prescribed function.
Okay.
Whereas if here, it's unclear. So anyway, I'm not here. Right, let me go on with the motivation. Obviously, cosmologically, we could wonder whether the universe just ends somewhere outside the observable universe. That's a pretty reasonable thing to ask, so it might end on some time-like boundary. When we think about black hole thermodynamics, in order to properly define it, at least without a cosmological constant, it seems to get a canonical ensemble, we need to put black holes in a box. And that was essentially Yorke's idea many years ago. And so in the Euclidean setting, at least, the standard construction, if you want a good partition function for something like the Schwarzschild black hole, is you have to put the system in a box. Holography gives us another motivation. The ADS conformal boundary, we're all aware, has played a very key role in physics we're interested in here, I think. Now, I would say immediately, the ADS, people talk about the ADS boundary, but the ADS boundary is not a boundary. The ADS boundary is an asymptotic region. It's a conformal boundary. So it's an asymptotic region you can conformally compactify. And when you do that, you get a time-like conformal boundary. But ADS is well behaved. It is well posed, and that was actually proven by Friedrichs in '95. So there's no problem with ADS dynamics. That said, in ADS CFT, we often regulate the conformal boundary when we do calculations in holographic renormalization with a real boundary, and then we think of introducing a real boundary that cuts off the conformal boundary, do our calculation, and then remove the regulator. And we think of that as the dual to usual renormalization in QFT. And so when you introduce that real boundary, you then do have to think it's, we probably do have to face up to the issue of actually, how do you impose boundary conditions there? And I think certainly in the case of non-conformal holography, things are probably much more complicated. I don't think mathematicians won't go near this, because the sort of geometries that are dual to BFSS and BMN don't have a nice conformal boundary at all. They're essentially singular in the UV. And so as physicists, we would always just cut them off, do some calculation, try and remove the regulator. So I think all of these issues of boundaries are much more pressing, actually, in the non-conformal cases. Anyway, so I think there's lots of motivation. What does well-behaved mean, or well-posed? So this is Denjo's question. So by well-posed, what we mean is that there's essentially some good map from boundary data to space of solutions, or boundary conditions to space of solutions. So the Einstein equations provide some map from boundary conditions to solutions, but in general, we think of differential equations as doing that, whether they're hyperbolic or elliptic or parabolic. So let's be very schematic. Supposing we've got some domain omega, we're solving some equation that looks like this. U is the function, or maybe a set of functions. L is some differential operator, or maybe some set of differential operators acting on U. And it could be nonlinear, although as I've written it, it looks rather linear. And there may be some sources F in that equation, or some other data in the bulk equation. And then on the boundary of omega, we're imagining it has a boundary. There's some other differential operator, maybe nonlinear, that acts on our solution and has to be equal to some prescribed other data. And so well-posedness is then basically the statement that given these operators and this data F and G, you can find a solution U such that one, that solution exists, obviously, you can find it. Two, it's unique. And three, and this is an important point, it continuously depends on F and G, the data. Okay, so that's what well-posedness means. If we want to be a bit more formal, equations like this you can think of as defining a map from some space of functions over your manifold that you're solving on to a space that's composed of a space of functions together with the space of functions on the boundary, where the map is just defined by these operators. So you put in a solution and then you compute the bulk operator acting on your solution and the boundary operator. So it's essentially the target here is the space of solutions producted with the space of boundary conditions. And then well-posedness is just then the statement that this map exists. Well, this map obviously exists if you've written down your equations, but it's invertible and the inverse is continuous. So that's the sort of more mathsy way to say it. So given a solution, we can invert this map. Given data, we can invert this map and get a solution. It's unique. And, how did I get rid of this fella? Why is he here? I can't see a pointer on my screen. Anyway, let me just say it's unique and it's continuous. So we've lost the bottom. Ooh. Never mind. So classical examples of well-posed equations would be obviously the Laplace equation on some bounded domain with, for example, Dirichlet boundary conditions, the Wade equation as a Cauchy problem, but with Dirichlet boundary conditions on some time-like boundaries. So maybe I should draw that. So we're thinking of the Dirichlet problem. We have some Cauchy data at t equals 0, and then we also have some time-like boundary where we might specify, for example, the value of the field, Dirichlet boundary condition. And a problem like this is called an IBVP problem in mathematics. That's an initial boundary value problem. And I can never get the boundary and the value the right way around. Anyway, so I'm not sure why they call it that exactly, but they do. Classic examples of ill-posed equations are, for example, the backward heat equation. Another classic example is the Laplace equation as a Cauchy problem, meaning supposing you tried to solve not the wave equation in this domain, but supposing you tried to solve, normally if I solve the Laplace equation here for some function, I would prescribe u on the boundary. I would give u on the boundary, and then that would determine a solution in the interior, but I could equally think of specifying u and the normal derivative of u on some portion of the boundary, and then trying to evolve that into the interior. And that is, as we know, ill-posed. So that's a classic example. Now, I'm going to go over the proof of why that's ill-posed, because we're going to use a very similar technique to show that this Lorentzian conformal boundary condition is ill-posed shortly. So let's think of the Laplace equation now on a two-dimensional half cylinder where we've got a boundary at x equals 0, x positive, and there's some angle that takes us around the cylinder base. And what we're going to try and do is solve the Laplace equation. So our Laplace equation is here. And we're going to try and solve it prescribing the function and its normal derivative on this surface. Okay. Now, we shouldn't be able to do that, so let's see where it fails. So we'll assume for contradiction that it works. So then we would have this map T, whose inverse exists and maps us from this prescribed initial data on this surface to the space of solutions, and that would be continuous. Okay, so it exists, so we can, for our f and g, there exists some bulk solution, u. So let's take that solution and let's add to it another set of solutions here, labeled by n. And it's, you know, if you've ever played around with the Laplace equation, it's completely obvious this is a solution of the Laplace equation. It's harmonic in theta, exponential in x in the other direction. And there's some n here, which parameterizes wave number in theta. And we're going to, because it's a linear equation, I can always add this with any coefficient I like, and I'm going to choose this coefficient, e to the minus root n, which may look odd now, but it's crucial. So this is a sequence of solutions that we think of labeled by n. And the initial data for that sequence is just, well, if we calculate u and u dot, we just find that the initial data fn and gn, which is u and u dot, are given by this. So that's the initial data sitting at x equals 0. Now, the key point here is that as we take n to infinity, this e to the minus root n kills these cosines, obviously. And so what we see is as we take n to infinity, fn tends to f, gn tends to g. And if we were being more careful, we would say in some function space like ck, the ck norm would vanish between fn and f. So fn would limit to f, gn would limit to g in, say, ck, or in smooth functions. I mean, this works for any k, so it certainly works for smooth functions. So what we see is that in the limit n goes to infinity, the initial data of the sequence is tending to the initial data of the solution u. However, clearly, if we look away from that boundary, x being positive, for any positive x, e to the minus root n, e to the plus nx diverges. That's why we chose root n. And so you can see immediately for any positive x, clearly UN does not converge to U. Okay. Now, what does that mean? So if we have a continuous function, so if this is the domain of the function, one definition of continuity at a point, say x naught, is that if I construct a sequence that limits to that point, and I have a function over this space, let's call these xn, and I look at the function evaluated on that sequence, that should tend, if it's continuous, to f evaluated at x naught. That's a definition of continuity. Okay. And so what we're seeing here is that as we think of this space now as the initial data, so this is f(g), this is fn gn, we have initial data that's tending to the sequence tending to fg, but the solution, which is the function acting on that initial data with this T inverse, the solution un is not tending to the solution that lives there, u. And so that shows that this map T inverse is not continuous. That's how you prove that the Laplace equation with these boundary conditions is well posed. So I think that's a very elegant proof. I think it's due to Hadamard. So if you learn nothing else that you didn't know that, it's quite a nice thing to know. Let's talk about the Euclidean or Riemannian context now for a little bit, and then we'll return to this Lorentzian case and make a similar proof to this in this Lorentzian case for these conformal boundary conditions. So in the Riemannian setting, as we said, York introduced boundary conditions in order to talk about the canonical ensemble, and there you want to fix on the boundary something like the size of the Euclidean time circle, and maybe if you're thinking about spherical black holes, the size of the two-sphere. And as you're probably familiar, the usual Schwarzschild solution is still a solution with those boundary conditions. But it turns out there are then two solutions, a small black hole and a large black hole. The small black hole is problematic thermodynamically because it has negative specific heat, but the large one becomes a good saddle point. And so you can develop the canonical ensemble for gravity. And Hawking and Page had actually previously shown that you see the same phenomena in ADS. That was actually prior to York. I don't know if it inspired him, but so if we took York's construction seriously, rather than just writing down the Schwarzschild metric, we would really be saying we want to prescribe the geometry of the boundary. We want to fix, for example, the size of the Euclidean time. We want to fix, say, a round sphere on the boundary. Maybe we want to deform it. That's a Dirichlet condition. That's fixing the induced metric on the boundary. But some time ago, these mathematical physicists actually argued that problem is not well posed. So they were looking at heat kernels, and they were looking at heat kernels for the graviton or the linearized gravity, and found problems with it and tracked that down to the fact that the linear operator isn't well posed. And then Anderson, the mathematician, the geometer, sort of later had a long discussion of this, and on the one hand gave a nice interpretation for why these Dirichlet boundary conditions are not well posed, and also then came up with a set of boundary conditions that are well posed. And they are, instead of fixing the induced metric, so the induced metric on the boundary we'll call gamma mu nu. So gamma mu nu is the induced metric on the boundary. He says don't fix that, fix instead the conformal class. Now, the conformal class is fixing a metric up to a Weyl rescaling it that's a function of where you sit. So two metrics, gamma mu and gamma mu prime, will be equivalent if there's some function omega such that they're related by this function. This should be a positive function, but it's a function of the boundary coordinates. Okay. So you're almost fixing the metric up to a local scaling, And then that last bit of information is, instead of fixing that local scaling, which is sort of what you do if you fix the induced metric, instead, he says, fix the trace of the extrinsic curvature. Now, the extrinsic curvature you can sort of think of like as the Neumann data for the metric. It's like the normal derivative, roughly, of the metric. And so this is just taking the trace of that and fixing that. So, or maybe if you've got the more geometric language, it's the trace of the second fundamental form. So this was nicely reviewed by Witten in 2018. I think lots of people think that Witten sort of invented this, but this is all entirely review of the earlier work. And these conformal boundary conditions are very natural from the perspective of holography. In holography, when we have an ADS conformal boundary, precisely what you're allowed to prescribe there is the conformal class of the boundary metric. That's how conformal boundaries work. And so the geometry is only defined up to Weyl scalings of that conformal boundary. So in some sense, if you actually wanted to think about regulating ADS, so here is the ADS boundary, you know, we can write it, say Z is 0 in usual coordinates. If you cut off your metric at some finite region, you could prescribe the induced, the conformal class of the induced metric on this, cutting it off. Now, at the conformal boundary, slices have a particular value of the extrinsic curvature. It doesn't diverge, it's got a particular value. So if you cut it off, it will have a different value. And then what you would do is you would take, in order to tune this to the boundary, you would hold the conformal class fixed. You would tune K to this asymptotic value, and then this boundary would slowly go to the conformal boundary. So that's a very natural thing, and of course what you're doing is you're tuning K, you're keeping fixed the thing that in the end will be the boundary data for the conformal boundary. So it's nice from the point of view of holography. There is some intuition, which I have to say I only really understood relatively recently. It's not particularly clear when you read any of the Anderson papers or even Witten's review. It's sort of in there, but in a rather obscure throwaway comments. The intuition for why the Dirichlet boundary condition is bad is really very simple, actually. So supposing we have flat space and we have a flat boundary. So we have the half space. So considering space out here, and we want to just prescribe a Dirichlet boundary condition on this type, this is Riemannian on this hypersurface. Let's just take this to be a usual Euclidean flat space, and this is just a slice, say x equals 0, so this is flat. So then the extrinsic curvature of this vanishes. It is all just uncurved intrinsically and extrinsically. The point is that if I instead slice my space-time taking a slightly deformed boundary, so let's say that was x is 0, let me instead take x is epsilon delta x. Delta x is a function of the other coordinates. So linear order, the extrinsic curvature gives the change in the metric when you deform your surface. So because that vanishes, a very simple calculation shows you that if I just perturb this position of this boundary slightly, to linear order, the metric is unchanged. But the extrinsic curvature does change at linear order. So this new metric here will have an extrinsic curvature that doesn't vanish. It will be linearly given by derivatives of this function. Sorry, Dan Jody, this is maximally inconvenient for you. And so what that's showing is that if you fix this metric to be flat, there are different infilling geometries right down the region. It's completely obvious. And that's why that problem can't be well posed. So it's really very simple intuition. Anderson's papers have a much more sophisticated sort of analysis version of that. So let me just tell you quickly about these boundary conditions, these conformal boundary conditions, and just tell you that there's actually a natural generalization of them. of Anderson's boundary conditions. If we just take the Einstein-Hilbert action, when we have a boundary, we're usually told we have to add the Gibbons forking term, okay, which looks like this. It's here, this is the gamma again is the induced metric on the boundary, K is the trace of the extrinsic curvature. And when you vary all of that, you get some part that is the bulk Einstein equation that we know and love from varying this. But you have to do some integration by parts to get that. And those surface terms combined with this surface term in the action generates you this term. So this lives on the boundary. This is the variation of the boundary metric. This tensor here, T, is what's called the Brown-York stress tensor. And so if you impose the bulk's equations, this action is indeed stationary if you fix the variation of the boundary metric to not vanish. That's why we introduce the Gibbons-Hawking term. However, as we've just said, even though all that variation works, the PDE system is ill-posed. But there's something very natural you can do, which is to just say, well, why don't I take a different coefficient here? Not 1 over 8 pi g, but something else. So let's take theta over 8 pi g. And it turns out that if you do that, what you are fixing instead is, rather than Dirichlet boundary conditions, you fix the conformal class on the boundary and this condition where gamma to p is, that's the determinant of the boundary metric to some power p. That power p depends on this coefficient through the number of dimensions like this. And it's that weight, that sort of measure weight times the trace of the extrinsic curvature. So in the case of p equals 0, this is just fixing k on the boundary in the conformal class. That's Anderson's boundary condition. But if you, for various values here, you get a different boundary condition. Let me not say more about that, but that's what I'll call the generalized conformal boundary condition. So you fix the conformal class, and you fix not just k, but more generally, you can fix the determinant of gamma to the p times k. So in our work, we actually develop, you can do black hole thermodynamics, you can get a partition function, and in fact, there's actually some utility in doing this versus Anderson's case, because what we actually did was we looked at fluctuations about the black hole saddle points. So what you want, really, if you've got a good partition function, you imagine, for Dirichlet, you have a small and a large black hole. The small black hole doesn't play a role in the thermodynamics because it's got a negative fluctuation about the saddle point. So it really should be interpreted more like a tunneling instanton. Whereas if the large black hole doesn't, and what we looked at fluctuations with these Anderson boundary conditions and these generalized ones, and it turns out in the Anderson boundary conditions, both the small and large black holes have an additional negative mode fluctuation. So they don't give you a stable partition function. Neither of them are good. Whereas if you take this p that we introduced, p is 0 as Anderson, but if you take p to be bigger than a sixth in 4 dimensions, it turns out that actually the large black hole then can not have any negative modes. So then you do get a good partition function. So actually, remember, Dirichlet is bad as a PDE problem, so you shouldn't consider Dirichlet. Then Anderson is good as a PDE problem, but actually, given this analysis, is bad in terms of defining a partition function because there are these negative modes. There isn't a stable saddle. And these generalized ones do allow you, in principle, a stable saddle. So I'm not sure what to do with any of that, but it's sort of interesting. Note that this is, you've probably heard about the conformal factor problem in gravity. This is not the conformal factor problem. That's something quite different. Yes.
Question.
Yeah.
Don't like to do these path integrals with the fixed area things.
Right.
Is it saying that that's always defined?
Well,
I'm trying to understand.
I think that's Lorentzian, right? So yeah, I mean, a lot of
sometimes it's Lorentzian,
sometimes it's. I mean, in the Lorentzian case, this is all Euclidean. Yeah, this is all Euclidean. Okay, so let's turn to the Lorentzian case. So at least in the Euclidean case, there are some nice boundary conditions you can write down. They actually do give you canonical partition functions that seem somewhat sensible. What about Lorentzian? So without boundaries, gravity was famously proven to be well posed by Madame Choquet-Bruhat already in 1952. And so again, we want to consider it in this setting where we have some Cauchy surface at time t equals 0, and then some time-like boundary. And so that's this initial boundary value problem, IBVP. And we want to specify some conditions on this time-like boundary. The natural one to specify is Dirichlet, of course, but as we've discussed, essentially for this same reason, the same argument applies there. That's not going to be well posed. And for other boundary conditions, this is very, very murky. So there's been a lot of maths work on this, partly motivated in numerical GR by wanting to introduce boundaries just to regularize infinity in simulations. The ideal thing would be to have outgoing wave boundary conditions, totally absorbing boundary conditions, so that you can cut off your black hole binary problem at some finite distance and completely absorb and measure the outgoing gravitational radiation. That would be the ideal situation. And so there's been a lot of sort of work on this, but interestingly, there's almost no cases where what I would call geometric boundary conditions have been shown to be well posed. So a lot of the mathematical work is work where you fix some gauge, you work with that PDE system, you impose some boundary conditions. You maybe prove well posedness, but the boundary condition you land up with is inherently fixed to the gauge. And you can't phrase it in a gauge invariant way. So it's not a geometric statement about the boundary, it's a statement that only applies. You're not fixing something simple geometric, you're fixing something very complicated that is gauge dependent. So maybe if you're doing numerical GR, it doesn't matter, but as a sort of, we really should be interested from a formal point of view in boundary conditions that would be phrased geometrically.
So this is specific to numerical GR?
I'm just saying there's been a lot of maths work on well-posedness of Einstein equations with boundaries, but in a lot of cases where boundary conditions have been proven to be well-posed, they're not of the nature we would want. They're not geometric, they're very much just pure PDE. They're boundary conditions that work for some particular gauge, but they're not fixing natural geometric data. Yeah. So perhaps if you're interested in simulating and you just sort of want to suck it and see, you want some well-posed system that you can put on a computer because you think it'll be well behaved, and you'll just see what happens at the boundary. These are, that's sort of the motivation for why there was a lot of work. But it's not the boundary. It doesn't give you any control over the geometry of the boundary. That's the problem. So, I mean, people, I think, tried to look at geometric boundary conditions, but just failed. The Dirichlet boundary conditions, which are obviously a geometric condition fixing the induced metric, have been argued to be bad only in 2020, although I think people obviously thought they were bad before that because people had obviously tried to prove they were well posed and failed. Again, essentially for the same argument in the Riemannian case, although there may be more to that, which is related to this probably I had on the very first slide. I'll say something about that later. But this is work of Anne and Anderson. And until recently, there was nothing on the Lorentzian version of these conformal boundary conditions. That's the natural thing to then think about. If you want geometric boundary conditions, if Dirichlet has failed, why not think about what works for Riemannian? Otherwise, the only geometric boundary conditions that have been proven to work are what are called totally umbilic boundary conditions, where the extrinsic curvature of the boundary is related by some constant to the induced metric of the boundary. So if you fiddle around with Randall syndrome branes, for example, this would be a vacuum Randall syndrome brane. But apart from that, there's no result for boundaries. So recently, so this is March, Ann and Anderson put a paper on the archive with this title, Well-Posed Geometric Boundary Data for General Relativity, Conformal Mean Curvature Boundary Data. We call it conformal boundary data. And in the last line, they say, with the corner angle included, we prove well-posedness of the linear problem in smooth spacer solutions for this system. So what they're showing is not the full nonlinear problem is well-posed, but this is a long paper, sort of maths analysis, geometric analysis, showing the linearized gravity problem is well-posed or claiming to. Okay. And certainly, if you want the nonlinear problem to be well-posed, the starting point is to look at the linear problem. So now I'm going to argue that it isn't well-posed, and I'll show you how to argue that. So we're going to consider linearized gravity for perturbations in a static cavity with a round spherical boundary. So a bit like this picture here, think of a spatial ball producted with time. And on the surface of the ball, we want to impose a boundary condition, and we want to impose these conformal boundary conditions, or generalized conformal boundary conditions. Okay. And then we want to start with some Cauchy data and evolve with those conformal boundary conditions. That's the linear problem. So we're going to write Minkowski obviously infills this as a solution, and then we'll look at perturbations about that. So we write Minkowski in the usual spherical coordinates. And then it's natural to introduce spherical harmonics, which are obviously solve the usual eigenvalue problem on the 2-sphere here. And we'll take our boundary for the unperturbed space to be at radius 1. We can always do that without loss of generality, so it's a round sphere with radius 1, but you can always, this is vacuum gravity, so you can always do a scaling and get any radius you like. So for simplicity, we're going to look at perturbations given in terms of spherical harmonics, but we'll restrict the azimuthal dependence to be trivial. So we'll look at YL0 rather than YLM, because that's enough for us. And I'll write f of theta is the spherical harmonic, but we use a slightly different normalization in the paper. But f of theta is basically the spherical harmonic with m is 0 and normalized like this. It's just the Legendre polynomial in terms of cos theta. So now we're going to write our perturbation of the Minkowski background as given by a tensor HAB. We've got a perturbation parameter epsilon, and we've got our amplitude CL. That CL will be very important. Think of that like in this Hadamard example we had much earlier. That's like this e to the minus root n we had. So that's how we're going to use it later. It's very important because it's a linear problem. If I've got any solution HAB, I can always scale it obviously by whatever I like. And then we'll be thinking of a sequence labeled by L, labeled by this azimuthal, angular dependence.
So in essence, you're just looking at the Lichnerowitz operator.
This is exactly the Lichnerowitz operator. Exactly. That's right. Yeah, this does just a linearized gravity. That's right. So yeah, so I should say the Lichnerowitz operator with these boundaries.
Yes.
Yeah. So we construct our perturbation. I don't want to give the impression there's no technical details. I'm sure you don't want to see all the technical details. So I'm going to go very quickly over this, but if anyone is interested, I'm more than happy to discuss it in gory detail. But we write this perturbation in terms of 2 parts, a physical part and a gauge part. I don't know how to...
It's visible on this screen.
Oh, it is visible. Okay, fine, perfect. Although I can't point to the screen.
Yes.
Okay. Physical part. So we have our physical part, which we write in terms of harmonic time dependence. This is very usual if you look at GR. Harmonic time dependence, our spherical harmonic angular dependence, and then there's some functions delta B, delta HR, delta L, delta HL, and HT that depend on the radius. So this is a particular set of modes. And there's also a gauge part, which we can talk about in a minute. But this tensor S ij is just built from the round sphere metric and from the spherical harmonics. This, if you plug it into the Einstein equations, has a slightly nice property that most of these functions are determined algebraically in terms of the remaining one, delta b. So there's no integration constants and eliminates these. And then everything is determined basically by this last function, which obeys a second order simple linear differential equation, whose solution is given in terms of Bessel functions. So in particular, it's this. It's some power of r times a Bessel function. I've normalized it in some particular way that we use in the paper, but it's not terribly important. There are, of course, two solutions when you solve an equation like this. One of them is singular at the origin, r equals 0. One of them is regular. This is the regular one. So taking that regular one, yeah, not far off. Taking that regular one, the last bit of this, you might wonder why we've added that. If you actually then ask, okay, well, we've taken a regular solution here to delta b, is this tensor smooth at r equals 0? It turns out it isn't, but it's smooth up to gauge. And so we just add a gauge part in that makes this whole thing smooth. So this gauge part is entirely determined by this, and therefore by delta b and by this functional form. So this whole thing, there is just one mode there, and it's given by this, and I can multiply it by any constant, but that's it. There's just one perturbation mode. So this is the gauge part, but don't worry. But it is important that this tensor, this perturbation is now completely smooth. You go to Cartesian coordinates, it's a completely smooth tensor. There's a second part of our perturbation, this gauge part, which is basically, it's generated by some vector field, which again has harmonic time dependence and spherical harmonic theta dependence. And there's some free functions in there. And you pretty much, you can do whatever you like. It's pure gauge. You want to keep things smooth at the origin. But other than that, these are completely unconstrained at this point. And the reason we add that in is so that we can impose the boundary conditions nicely. And in particular, it allows us, when we perturb, to keep the boundary at r equals 1. You have to be quite careful with boundaries in GR, because obviously, as you deform the metric, it may be that the boundary is forced to move. But if we build in, if we allow there to be this gauge freedom in our solution, we can use it to fix the boundary to be at r as 1. So I don't want to go through, I'm happy to go through these details, but I think in the interest of time and everyone's sanity, let me skip them. But just say, if you go through the analysis and impose the boundary condition we want, that the conformal class of the boundary is not changed from the background case, and that we preserve this condition on the trace of k multiplied by this weight, so that's not perturbed, then you get some, at the end of the day, you get some condition on omega, relates omega to L in this way. So you expect there to be, this is the usual thing with second order PDE. We've got some smoothness condition at the origin, we've got some other boundary condition. There's usually then a relation you have to fix up, given by the sort of spherical eigenvalue L and its relation to omega, the time dependence. Now, it was observed that in the conformal case, p equals 0 by Aninos, Galante, that there are instabilities. There are solutions here where omega is complex. So remember, the time dependence here is e to the I omega t. So if omega has a negative imaginary part, this will have a growing real time dependence. So it was observed that there were the small L instabilities, and they made a comment that they exist for large L. In our paper, we actually analyzed the large L dependence in some detail, and you can solve this asymptotically in the following way. So omega asymptotically goes like L when L is large, plus an L to the third direction, where that coefficient gamma is a solution to this equation. AI is the area function of the first kind. And maybe I should come over here because this is important. There are real solutions to this that are uninteresting, where gamma is just negative, real. But there exists, as far as we can see numerically, because you can solve this very easily numerically, you can see a complex conjugate pair of solutions where this is actually complex and has an imaginary part. And you take the appropriate one such that omega gives you an instability, and that then generates an instability. So this is an instability, if you think about it, for high L, so for large angular dependence. And that looks odd and bad. So for every large L, the claim is, not the claim, you can go and solve it. For every large L, you find an unstable mode, and this is, you can numerically determine these modes directly from this condition up here. You can just numerically find roots of that, but they agree you've got to go to quite high L for this asymptotic approximation to work well, but it works well. And in fact, in our paper, we proved that for sufficient L, these modes really exist. So it's not actually good enough to have an asymptotic solution. That doesn't guarantee existence of the actual solution. You can prove it.
Does it mean that the system wants to rotate?
These are, let me see. Does it mean that the system wants to rotate? No, I don't think so. These are standing modes, I think.
The instability.
Sorry, you're right. Does it mean? I think it more means that the boundary wants to crumple rather than rotate. Yeah, maybe I have to think about that. But certainly it wants to crumple. But whether it wants to crumple and rotate, I'm not sure. Anyway, to sort of speed things along, at large L, what you actually find if you look at this wave function that governs everything, that lives between 0, the origin, and 1, the boundary, is that these wave functions localize near the boundary. This is L increasing up to 1,000. And that's again telling you this instability is associated very much to the boundary. In gravity, we've got to be a bit careful. Maybe it's just gauge. Maybe it's not a real instability. But in fact, if you calculate components of the Riemann tensor, linear order about flat space, the Riemann tensor components are gauge invariant. And this component, for example, its linear perturbation is just given in terms of delta. So it's f of theta, angular dependence, the harmonic time dependence, and delta. So it's a physical effect. So, sort of coming to the conclusion, then, what do these modes mean? Well, the point is, let's now make the choice of normalization of these modes, e to the minus L to the 6th. This is the sort of analog of e to the minus root n in this Laplace example I gave you earlier. E to the I omega t at large L has an instability in time which grows like this. It grows like L to the 3rd with some coefficient. This is the problem. So if we multiply our perturbation by a behavior that goes like e to the minus L to the 6th, which is weaker than this L to the 3rd, the key point is that CL goes to 0 exponentially as L goes to infinity. And in fact, any polynomial of L multiplied by this will go to 0. But if we multiply by e to the I omega t and t is positive, that diverges. Exactly like in a Hadamard argument. So what we see by looking at the sequence of solutions is that the sequence has initial data at t equals 0 that vanishes as L goes to infinity. And in the paper, we show that quite carefully in smooth norm, CK norm. But for t greater than 0, the perturbation does not converge to 0. And a gauge invariant like that Riemann tensor component certainly doesn't converge. So the linear problem obviously admits the 0 solution. We're looking at perturbations about it, but we've got a sequence of perturbations whose initial data converges to 0. The solution doesn't converge to 0, and therefore this inverse map that we were talking about for well poses can't be continuous. Because we know there's a 0 solution, but I've got a sequence going to the same initial data which doesn't limit to 0. What about Ann and Anderson's work? Well, we obviously were a bit worried because this was a very formal paper, very long analysis, and so we sent this back to Michael Anderson, who was very kind and had a discussion with us, and looked more carefully and basically said that actually their paper didn't establish well-posedness. It established it established the inverse map, uniqueness and existence for the inverse map, but they didn't show continuity. And in fact, according to him, they tried to show continuity, didn't. And the reason they didn't is that it isn't. So I think the conclusion is that their paper, whilst it's interesting, they certainly had theorems in there, there actually wasn't a theorem that said that inverse map was continuous.
So it was just mistitling?
It was, yeah. So basically, there will be a revised version according to Anderson. And the analysis in the paper is not wrong, but the conclusion drawn was wrong. So anyway, in conclusion, the obvious geometric boundary condition, which is Dirichlet, seems to be, well, is ill-posed for both Euclidean and Lorentzian signature. So that's the first takeaway, and it's strange. There is recent work again by Anna Anderson, this is even more recent in the last few weeks, that suggests it may be that the Lorentzian Dirichlet problem is well posed in certain situations. It certainly isn't if you have a flat boundary for the reasons I've described. But perhaps if you've got a spherical boundary that's positively extrinsically curved everywhere, it's okay, perhaps. I don't think that can be true, but they've claimed to prove it. Okay.
Without continuity.
I don't know. I just don't know. So I'm not. I think it's surprising. It's true, but it may be true. And actually, Witten made some remarks about this in his review, that not claiming that it would be well posed, but claiming that even if it isn't well posed, maybe it's still okay for thinking about quantum gravity, or for maybe certain properties of the PD system is still reasonable. I'm not. I think it's just unclear. It's very murky. In the Riemannian setting, whilst Dirichlet is bad, there are these conformal boundary conditions that are okay, and Anderson and then these generalizations that we introduced seem to be okay. And this generalization does actually allow you a good partition function for black holes in a canonical, whereas Anderson's didn't. But in the Lorentzian, rather surprisingly, it seems that they are bad as well. And so, the end conclusion is boundaries in gravity are rather complicated, and it's not quite clear how to introduce boundary conditions. Apart from this sort of very simple brane boundary condition, there doesn't seem to be any other known boundary condition in the Lorentzian case. And that's a surprising state of affairs. So I'll end there. Thank you.
Thanks a lot for letting me give this talk here. Though some of you would have known part of the work, most of this because it was done mostly in DIAS. Towards the late time I was as a postdoc here, and also in Trinity. So I'm going to talk about this Instantons and Vafa Witten theory. And this major part of this talk is on my paper with me and Jan Mansford. Jan is here now. So if there are more questions, you can also ask him. And let me just get a little familiarized before I start with this. Okay. Thanks. I can't fit this picture properly. The basic idea of this picture is that there are lots of relations and connections between physics and mathematics. In one side, I have basically drawn the physics objects like black holes, string theory. Am I audible, by the way?
Yes.
Black holes and the string theory, mostly string theory, black holes, also like string dualities, M theory. There are lots of terms which are not written also, supersymmetric field theories and all. And on the right hand side, there are some questions that we're still asking, like whether we can think of these as like the well-established objects are like instantons and Superyangas theories. These are comparatively very more well-established objects. but we're still asking questions about, say, can we talk more about, say, characters of conformal field theories from very similar objects. And in the middle, I've basically written the objects which we encounter in mathematics. And I have removed the terms, I have not used too much of the terms which are involved in algebraic geometry and topology, but these are mostly from number theory. So one object would be class numbers and partitions, modular and mock modular forms, and also there are like objects like, say, modular bootstrap and Vafa invariants in these contexts. But I'm going to mostly stick to the right side of this picture, that is this instantons and super Young's theory, and how we look at the mock modular forms associated to this. So first, let me describe what I mean by instantons. So, say in quantum mechanics, we may have several vacuum solutions. Like if our potential is like this Mexican hat, well, in 2 dimensions, we only have, say, 2 vacuum, which are the lowest points of the energy. And then there are certain solutions which can interpolate between these two vacuums. And these are basically given by what is known as instantons, and we can have several zero energy solutions of this family. One interesting point to note here would be this, that the Euclidean action, if we Euclideanize the action, then we get a non-zero minimum of this, for these vacuums. The next thing that I want to talk about would be the relations of these instantons in quantum field theory. Professor Nam here has been one of the inspirations behind this project himself, and he was also involved in very early works when people were trying to understand the QFT context for these instantons. So these were first studied in the context of chiral anomaly and magnetic monopoles, and these were done in the early 70s by Tuft and many other people. A complete construction using linear algebra for these self-dual instantons in the Young's theory, in basically this Euclidean sphere S4. These were done by Atiyah, Drinfeld, Hitchin, and Manin in 1978. And there was a more elaborate paper written by Drinfeld and Manin around the same time, explaining the full procedure. The generating function of Euler numbers of moduli spaces of instantons on R4 with boundary conditions such that the gauge potential AI would be going like 1 by R squared, and the field strength would be 1 by R cubed when you go to large radius. These were computed by Nakajima in the 1993. Most of this talk would be based on certain predictions and some better understanding of this very well-known kind of a classic paper written by Vafa and Witten in 1994, and that's why I'm going to so that's why I'm just going to call this whole theory as like Vafa-Witten theory, because this is the paper which we are going to mostly be doing in this. So the idea behind this is that these are topologically twisted N=4 super Young-Mills, and partition functions in this theory, say for a given gauge proof, which I am writing here as G, mostly I'm going to take some UN or SU1, and the complete constant tau is expected to be modular forms. So if you consider this S duality, then under this you can take, say, tau going to -1 by tau, and G going to this Lagrange dual G, LG. So for UN, this is the same. So we expect that, especially when we are talking about gauge group UN or SUN, we are going to expect modular forms. I'll explain modular forms and all in briefly in a later few slides.
So there are three twists of N=4. So this is one of those.
One, 2 plus
This is not
1.
the geometric Langlands twist.
This is the 1, 2 plus 1, 2, and the interchange between that. So partition functions in Vafa Witten theories, I've basically abbreviated as VW here. So these are on different compact 4 manifolds and can be computed using methods in algebraic geometry. So given say a path integral where phi is basically set of all the fields that I have, and tau is given by this inverse of coupling constant 1 by d squared and some phase that related to the Instantons. Now the symmetries in this theory would be is basically this global R symmetry SU4 in the N=4 superangles. And there is this fundamental representation of this SU4. I have written it as a bold 4. It is identified as 1, 2 plus 1, 2 for the local spin 4. And this, I mean, for me, effectively, this what it does is that I don't require any more supersymmetric indices in this whole analysis. So all the indices that I will be writing are space-time indices, and even the SUN gauge group indices will not really be shown in the following slides. There is a SU2 which can interchange between this 1, 2 plus 1, 2 of this local spin 4, and this ends up being the global symmetry for these twisted series. So if you are looking at, say, the bosonic part of the action, I have the gauge fields AI. There are self-dual 2 forms BIJs and some scalars. For the instanton part, we'll mostly set these B's and C's to be 0. And there's also the fermionic parts, of course, with self-dual 2 forms and vectors and scalars. So the action, the bosonic part of the action, it's just given by this, and for the instanton part, I require this BC to be 0 and also this Fij's in the self-dual or the anti-self-dual form to end up being 0. And the instanton number, I am writing it as K, which is just this trace wave Fij. Now suppose we have a finite dimensional and simply connected gauge group like the SUN or G. The moduli space of these instantons remain finite dimensional, and the Euler character of this moduli space of these instanton solutions can be computed using these algebraic geometry methods. These are broadly known as ADHM construction because the original work of the Atiyah, Feldhitten, and Manin in the 1970s. For these complex manifolds like the CP2 projective complex plane, we would require another important theorem, which was called Kobayashi-Hitchin correspondence or Donaldson. These were proven by Donaldson, Ulenbeck, and Yao in the 80s. And the idea was that in one side, in algebraic geometry, you have these semi-stable sheaves, and in the other side, which would be relatively, like from the physics understanding, would be these Young-Niels instantons. And there remains a one-to-one correspondence between them. So if you know how to compute this number of semi-stable sheaves, you kind of know what are these Euler characters for these instanton partition functions. So just if you are looking at the simplest case of the gauge group is U1 instead of SUN. So these partition functions are just given by some powers of this Dedekind eta function, and where this power is basically given by the Euler character of the 4 manifold. on which you are looking at the theory. So for if you're looking at say K3, then you basically have 24, and if you are looking at say CP2, then you basically have 3. I'll just very briefly introduce these modular forms because I have to talk about mock modular forms a bit. So these are just some mathematical functions which lie in the upper half plane of the complex plane, and this tau parameter remains in the upper half plane. What is the best way to point? Shall I use this? Yeah, that's
the point of X on them.
yeah, this works, right?
Yeah.
Sorry, can I just ask, could you go back? I think I've just missed a point, sorry.
This one or
The partition, so this partition function, sorry, what is the partition function? It's the partition function of what, sorry?
oh, for this instantons. So you set these objects like this 0 and try to compute.
If U1 equals 4.
Yes, yeah, that's for the 1 by eta. The rest are more complicated, and I mean the computation actually goes via these shapes.
Right. Okay.
So you have basically a parameter tau in the upper half plane of the complex numbers, and f tau is a modular form of weight k if under some SL2Z
Just to
transformation.
clarify, the U1 equals 4 is presumably it's got the gauge field, but the fermions now are some sort of forms in this twisted setting.
I think so.
They're just it's closely related to Dirac-Kahler, I would imagine.
Sorry?
Yeah, I would imagine it's closely related to the Dirac-Kahler we started with.
I am not very familiar
In the
with
twisted
Dirac-Kahler. Maybe Jan can say it. Do you know what a Dirac-Kahler means? I'm not
That's
familiar
okay.
with that. Okay, so these are just some modular forms, and the interesting thing is that you have under this SL2Z transformation, SL2Z I mean like A, B, C, and D. They're just one after the other, and you have this C tau plus D comes with this power k, and this k is called the weight of these modular forms. In general, we'll be dealing with objects which have a little more, little more, say, freedom. So we can have certain phases here, which are written as say epsilon, and one of the examples is itself this Dedekind eta function, because Dedekind eta function also, if you take say c is equal to -1 and d as 0, you just have this -1 by tau, and you get this weight half, but then there is a factor of say square root of -I. So there are two basic generators for this modular group, full modular group, S and T. This notation is different from what it used to be apparently in the early 60s and 70s. Around that time, people used to just call them just the opposite. S transformation was called what I have written as P, and vice versa. This was, I don't know why it changed, but apparently in the very early papers, I have seen this name to be different. So we can have like some subgroups of SL2Z called gamma naught n, where I'll have this C element here, this 2-1th element becomes NC, it just becomes a multiple of this n. And in general, due to this this transformation property of this T, it leads basically say to tau into tau plus 1. And so you have kind of a Fourier expansion possible in this modular forms setting. So you can write f tau as some a in q to the power n with q as e to the power 2 by I tau. So since I've already spoken it a little bit, so and interestingly, modular functions will remain functions on torus, and S and T can be understood as T as some extra winding of one of these directions, and S can be thought of as the interchange of the two cycles of the torus. Now, if you have, say, since I spoke about this gamma naught n, say you have weight half modular forms in gamma naught 4, and the examples of these two are end up being very important for writing these class number generating functions. And you can just write them as some theta functions, and under these transformations, they kind of form like a matrix, and you can basically compute these matrix elements like 1, 1, 1, and -1. So the difference between modular and mock modular forms are like this: mock modular form has a non-holomorphic piece, say, I mean, I'm writing it as R here, which also depends on the complex conjugate of tau. And if I add this with its holomorphic piece, then what I get is this f hat. And this f hat object actually transforms like a modular form under this S transformation, say. So if I make tau into -1 by tau, tau bar into -1 by tau bar, I get back some weight tau to the power k, tau bar to the power some k bar, and I get this f hat back. But if I just look at this f tau, I don't get the full object back, but I do get something like which looks like an integral. I'll give you one example. I'll give you the generic functions or generic form of this R. So I can write R as some iterated integration on several variables, and there exists an object here, this G, which is called the shadow, and this G basically depends on this G basically is a modular form. So in the case of this class number generating function, this G itself becomes this theta. And so syntax example that we have is that of Eisenstein series, and Eisenstein series of weight 2, which is not exactly a modular form, but it becomes a mock modular form. And this R tau tau bar in that case can be written in this form. This it can be written as this -6 I by pi, and there is one. I mean, there's just one integral. So that there exists a notion of depth, and that basically means how many integrals are there here. So I can call this E2 as this depth 1 object. Now, a modular form needs to be bounded at all of its casts, and these casts basically criteria comes from this cast criteria basically says that it needs to have only, say, positive powers of Q in this expansion, and if a modular form is also called a cast form, in case this this bounded object ends up being 0. So if you write as a n q to the power n, and when tau goes to infinity, that means q to the power n would go to 0. So the first term in this expansion should end up being 0 for a cast form. Now the whole concept kind of generalizes to vector valuedness. So you can have modular or mock modular or cast forms in a more higher dimensional setting. So there will be many forms, and you can transform them, say, under this S transformation with a matrix MS, or under T transformation and an empty, and you get back a similar object. In general, this MT ends up being diagonal in most cases. There is yet another thing which comes in handy to understand very briefly. This is the notion of Appel-Lurch sums, because when we look at this computation from the sheaves, what we end up getting are certain Appel-Lurch sums in the process, and one can actually study the mock modular properties of these functions. I have not written exactly what we get, but broadly what it means is that you have a quadratic form qk in this numerator of this power of q, and some bilinear form with, or you can say just some linear function of these elements of a lattice lambda. And in the context of this Vafa-Witten theory, my QK and LK can be given in terms of these Chan classes, and these are, say, these small LIs LJ in the denominator. These are given in terms of, say, wild reflections of some simple roots of SUN. So I can just use the simple roots of SUN. So this would be, I mean, this lattice would be my root lattice of the SUN, say AN. Now let's look at some of the results of this Vafa-Witten theory for the gauge group of SUN. So we have, say, for the case of K3, the result is basically known very explicitly, and these can be given in terms of just these eta functions and some Hecke operations of these eta functions. You can just tau becoming some different multiplicative results. So, but however, when we look at more complicated manifolds like CP2, the SU2 results ends up being it ends up being mock modular instead of, say, modular. The eta function was a completely modular object, but it ends up being mock modular in the cases of, say, CP2. And there remains trade-off between modularity and homomorphicity due to some boundary of the moduli spaces. These were initially studied by Vafa and these other people. I cannot actually pronounce most of their names. So this was also very early in the early 90s, and very recently I have forgotten to put that paper's link here. Witten, Davolkar and Putrov, they wrote a paper, I think in 2020 or 2021 during COVID, and in that case they actually gave more explicit constructions of how this trade-off happens, how this holomorphicity ends up being, like how the boundary contributions are understood.
Sorry, can I just ask? So if you go back a slide, you said the K3 case.
Yes.
You just used the words. If we look at CP, the more complicated manifold CP2. Now K3 is very complicated. I would say CP2 is a very simple.
Yes.
So what's happening? Why is it more complicated?
It's basically the Betti number of CP2 is 1.
Yeah.
And when you have Betti number of a manifold as 1, then only these results become mock modular. And this is basically this trade-off itself. Like when it happens is when you have less freedom in some sense. So K3 has higher B2. I forgot what's the number. 20, 22, something. 22. Yeah. So K3 is fine. With if you look at even Betti number 2, I think it's fine. But just Betti number 1, the reason it's complicated, the results end up being complicated is this Betti number being very small.
But did you say it was something to there being a boundary of the modular space? Is that what you were? Oh, sorry, maybe I missed that.
No, the contributions are, I think, from the boundary of the modular space, which end up being problems here. So this holomorphicity needs to be treated.
I see, but you're saying when the Betti number is 1, it somehow changes the behavior of the boundary.
Changes the behavior.
Does it, in fact, just very naively, does the modular space have a boundary in K3?
I can't say this. I'm not sure.
Okay.
Because the K3 result ends up being just some Hecke operation for me. Right. So they are simple in that sense. But if you try to compute these class numbers from scratch, it's much more complicated. Okay. If Jan wants to point anything here?
Yeah, it's not so much the boundary of the modular space, but it's not the boundary of field space. And the Betti number which is relevant is the plus component in B2. So B2 plus is 1. Then you get a metric dependence. If B2 plus is larger than 1, you can kind of walk around the lobes and there's no metric.
I see.
Also, as the consequence of B2 plus is 1, there is a contribution of the so-called conglomerates of the theory. And that gives rise to a
There's some extra. So the result for this SU2, it was computed in the early 90s by Klyachko and Yoshioka, that the results would be given in terms of this class number generating functions with H4n and H4n minus 1. These are what is known as Hurwitz's Kronecker class numbers. So it kind of tries to compute some quadratic form with certain multiplicities. That's it. And this subscript here is refers to the magnetic flux or the Etude flux for this like the stress of it. I don't want to go through this more because I think I am at 11:16, so that means I have how much? But I started late, right? So I do have a little more. So anyway, so this HN basically computes some number of parameters of this kind of a quadratic form. And interestingly, this the earliest understanding of that this kind of objects will have mock modular behavior was done by Zagier in his very early paper in 1975. Around that time, I think there was no such connection made between instantons. I just want to point out one small thing here that I want to, in the next few slides, I'll be showing you some plots. And for those plots, what I plot is this mu n kind of objects, all these coefficients. And I don't take into account, because in this definition of say Z0 and Z1, say I have some inverse eta products. And these come from the point like instantons. In any of the slides later on, whatever I'll be showing, I'll not be considering this inverse eta functions. So all I want to look at is that I don't want to look at the point like instantons. I want to see how these mock modular forms are behaving. Sorry, please. That. So this is a plot of the ANs basically, and like you can see, you don't have to like bother too much about which number is what. It's not that well probably being reflected in the but the idea is that you can see that this whole structure remains extremely scattered. Right? If anyone who will look at this plot will not really talk about much of symmetry coming out of it. So all these green dots and red dots basically refer to one or the other of these coefficients of this Z0 or Z1. That's all it refers to.
So then these are coming from the presence of a magnetic field or the absence?
The magnetic flux being 0 or 1. 0 would be for the red one, and the green one is 1.
So this is how
and the plot is just general the instanton number n.
Okay, this is how the coefficients change as we turn on the magnet.
Exactly. Okay, if I just look at, say, if I am looking at, say, prime numbers for these objects, like if the n is prime, say this A0, and I'm just trying to do the plot, it still looks quite scattered. There are how many primes? Up to 400, maybe around 50 prime numbers are there. So this still looks quite scattered. This is also true for the other. However, if we look at this SU3 case, when my gauge group remains SU3 and I'm looking at again this on the CP2 manifold, I see the behavior to change. And one could compute, Jan himself computed this partition functions in 2017. There are some explicit forms for a generic SUN that you can actually compute, and these are all under the understanding of this DUY theorem. And the thing that we study would be this Apple large sums. So I don't want to focus much on this inverse etas, because if you have some inverse powers of etas and the weight of these modular forms or mock modular forms end up being negative, then the growth of these coefficients become enormously large. If n, I mean n basically grows like e to the power square root n or something. That's the average roughly behavior for all mock modular or modular forms. So one interesting thing to note here, that if we are looking at this this SU3 case, then the result from this F3 mu object would be some function coming out in the gamma naught 3 gamma naught 3 matrix, gamma naught 3 gamma naught 3 group, and not the full SU2 SL2 set. So one can introduce a vector valued modular form. This is not mock modular. This is purely modular form. This given by this M0, M1, and M2, and you can see that their expression does not have any dependence on the conjugate like Q bar. There is no Q bar dependency. And this mu, it's a weight 3 object, and this object has the same multiplier system as that of this mock modular form F hat of 3 mu. So if you replace this F hat instead of this M, you get the same numbers in this matrix form. Like you still get -1 to the mu e to the power pi I mu squared by 3 in the first line, and the second line also gives you this same factor. However, if you are just looking at this case of the SU2, you don't have an analogous modular form which has the same weight and the same multiplier system. So one can't really do what I'm going to do right now. Interestingly, the M0 object is the theta function on the E6 lattice. So we can define a mock cusp form where I just subtract this mu with this F3 mu with the correct coefficient between them, and that number I chooses an overall 1/3 for certain like other purpose. It didn't have much to do with it. These numbers were all divisible by 3, so I probably removed it. And so what happens is that if I actually want to what happens if I want to just compute these coefficients in the S0 and S1 like this, how these 3, 9, 21 and these objects would grow, if I want to see how that happens. So I can show this F3 and this S. And again, these green dots basically mean that these are for, no, sorry, let me just avoid these 2 slides. Let me just focus on this S0. So if you have, say, this small S0 n basically means that you have, you are looking at this cusp form coefficients and mu equal to 0. And for odd and even numbers n, there is the growth is generally slightly different, but the whole plot you can still see that this is quite scattered. Now the interesting thing happens if I just look at the prime numbers. So then these numbers literally end up being on very nice lines, and this is even better for the case of this S1. S0 has at least 2 lines. But S1 has literally just 1 line. This is the result for the prime computation. And the object basically grows as p to the power 3 by 2. But again, you see p to the power 3 by 2 is not going to be an integer, and we do get integers from all of these computations. But these are very close. By very close, I mean like the best fit curve will be like this. If you this was done up to 600, and I think we did a little larger, like 800 or something. The growth changes very slightly, like maybe 1.03 or something, but then it still becomes p to the 3 by 2. You can easily fit the curves very nicely.
Can you understand that at large value? Is there some asymptotic behavior?
Not yet. Well, actually, there is something that Catherine Brinkman and Janet Nazaroglu, they are doing, but they're trying to understand this F3 mu as this F3 mu as some kind of a mock Eisenstein series. This, I mean, we have not really studied it that far. But this growth was quite interesting for us. And if you just look at, say, without the primes, if you look at the full S1, then this is the plot. And this, you can just see that prime just forms a line with about 50 numbers there.
The coefficients of cost forms are famously hard to find.
No, I mean, there's a bound is still there. Upper bound is still there, but we don't know how the growth.
It's easy to get an upper bound, but to get an accurate upper bound is
Tight one.
Yeah, we don't have a tight one, that's true. So,
Asymptotically, is that curve an upper bound? Well, not an upper bound, but is it the case that, no, if you look at all of the numbers, not just the primes.
okay.
I guess maybe you can't go to higher values. I just wonder whether asymptotically, okay, I mean, there are points above that line, but maybe the extent to which they're above is bounded in some way.
I mean, the upper bound of these curves are known. That we can, I mean, we can
But
give
it's
a.
not sharp. There just is an upper bound. So I wonder whether this curve is almost an upper bound.
There are more points though above it. So it is not exactly an upper bound.
That's what I'm saying. Well, clearly there are points above it, but maybe the extent to which they're above it asymptotes to some, maybe maybe that curve plus 1,000 is an upper bound. Yeah, exactly.
That's possible.
Another thing which seems to be interesting, that there seems to be some kind of regularity if you shift the primes by 60. So the points above the line are sort of equidistant, and the lowest points are also some equidistant. So it looks like you have a conductor of 60 or something like that. Have you looked at that? Or?
You're reading the 60 from the higher.
Are there no 60 thing?
Well, this is.
I mean, when you look at distance, so it seems to be pretty regular. Of course, one should look at it in more detail. But normally in all this number theory, you have some kind of periodic behavior when you shift your primes by certain amounts. That's usually in class field theory. It might be worthwhile to look at it.
Is the calculation of these points very complicated, or is it very easy?
I mean, it takes time in the computer, so we don't have, and this cannot be used. I mean, it's very difficult to say use Python. So running time is quite high.
This is an expansion in Q of known functions.
Of some functions, yes.
So when you compute the Hurwitz numbers, you actually write the solutions explicitly, or is there a formula?
No, there are some generating functions for that. Explicit computation will take ages, probably. But there are generating functions for F3 mu that Jan computed in 2017. So that, but that has like several poles, some other modular forms, and some product objects. So it's not very easy to. There are other ways to compute this F3 one also, but they become even harder because there you are trying to solve certain like those can be actually put in Python, but because you are basically just looking at some bounds. And finding, say, integer solutions of some bounds which are lower bound and upper bound, many equations, but then the number of equations become very large. So I tried doing in both sides, but I think the best that we went was this 600 or 800, some stuff like that. We didn't really go beyond 1,000 for sure. That would be it's a computational question after this.
There's a closed formula for a given coefficient. Every once in a while, we work with experiments. The mathematicians, they are closed formula.
What type of plus one is it? Start with
No, it's some sum over, let's do symbols, divisors. It's like an Einstein series, but then more complicated. Sum of divisors to some power.
I mean, computation of the devices is itself, it's kind of this NP problem or something, non-polynomial in nature. So it's not, it still probably won't give like a very large number very easily. Okay, so here I just wanted to point out is that if we look at say just the Deligne bound coming from the like if an object was of purely modular form or purely cast form and did not have any non-zone over fixed behavior, then Deligne predicted some of its some of the upper bounds there, and we see that gets exceeded, and that gets exceeded basically because the major contribution actually comes from this integral part. When you write this F3 mu hat, there for a mock modular form you have some iterated integration, and that gives you the biggest contribution to this whole system. And if we just look at some like the rough estimates using saddle points, oh, okay, then one can find some of these upper bounds with this n to the power 5/2. And if you actually compute more systematically, like trying to say find the number of lattice points covered by say a hyperbola of a particular distance from the origin. So that kind of computation gives you something like an n squared.
So do you think that this bound is best possible when you look at your numerical data? Is the bound close to the actual behavior? Or could you...
The bound is higher than the actual behavior.
Okay. So what would be the best possible exponent when you look at the data?
It looks like that.
This is about something like 15,000 or 16,000, say. And this is the highest one that we got around 550. So 550 to the power, and it should be close to this 3/2 only. It's not very far from the 3/2, say. But
okay, yeah.
Let me just move to a little bit because this is a kind of described quite a bit. So the idea is that
the theorem would be that there are a finite number above that curve.
so there are many theorems in mathematics which say something like this.
As you go to infinity.
Yeah, there are many theorems in mathematics which actually say there is a finite number, but no one knows what the finite number means. Yeah, I mean, even say like this divisor function. Divisor function, you're just computing summing the divisors with one part only, so E2. So that function, I think it goes, I mean, it has to be greater than 1, but then you can find the finite power extra, but no one knows what that finite thing is. I asked many people for that. It actually, no one given me a better answer than this. So this is basically like if you try to find, say, how many points are within this kind of hyperbola, and of course they have to be bounded by some cones, and these cones actually lead to the fact that one gets a mock modular form. So there needs to be an extra bound coming from some cones, and if you found how many points are there. And if we just had one negative direction to do this computation, which needed this cutoff, like a hyperbola say, then that number is better known, like it can be estimated by n squared in this case. Instead of 5 by 2, this is still a half improvement, but this is not that generic result. So if you have, in general for SU case, we have 2 negative directions, and in that case, but still the 2 negative directions also the actual bound seems much lower, but we get here. The last point that I want to make here before the concluding is one of the other predictions by Vafa and Witten in that original work was about the holomorphic anomaly. And the prediction was that if you take if you want to see the holomorphic anomaly behavior, you basically take this tau bar derivative, and you get back you basically get back the instantons of lower ranks. So this is the, I mean, I've written this schematically, it's not explicitly all the same thing. But so if you say start with the instanton of rank n, you get the instanton of rank n minus k in the holomorphic anomaly. Yes, I'm close to completion. So to achieve this, one would require in the Appel-Lash sum object that one can write this g hat. I have not described the full definition of g hat, but one can write this object as some theta function, and this theta function involves your this iterated integral. So this is not a pure theta. This is this mock modular theta in that sense. And then you also get back this lower rank instantons. And this we have seen in our recent work, which is hopefully going to be published this year. And that we can explicitly write this g hat object as one term coming from this holomorphic definition, and then one term coming as this theta. This theta is this indefinite theta, which is contains my iterated integrals, and this lower rank. There is this extra term mu, which is basically going to give me some conjugacy classes. So it's not going to be just one instanton, but several instantons computed under this conjugacy classes, and one needs to still find out. So lastly, I just want to conclude with 2 things. One is that like the original picture that I showed, I don't think I have it here anymore. So was that like, there was one question about conformal field theories, and this was also a part of the prediction of Vafa and Witten in their original work, that can we read off conformal field theory characters from these instanton partition functions, say in one, like if you think of M dual, M theory, so you have conformal field theory in one part of the moduli space, and in the other part you can read them off as instantons. So is there a way to do that? So that would be a very nice thing to understand. And in fact, if you look at the superconformal characters and of say this n equals 2 or n equals 4 superconformal characters, and you also look at say the class number genetic function coming from these Appel functions, so these end up being very similar functions. So maybe under certain conditions they do match. So we are trying to understand this for like higher rank age groups, and if there is very significance to the coefficients of this Fn mu or Fj mu in general. These are what I guess like Lucas, Ringman, and Natharu seem to have some better intuition here. Thank you.
So first of all, thanks to organizers for inviting me. I've been given the really hard task of standing before lunch, so I will try to be quick. So basically what I'll say is a small part of some work that we've been doing with my collaborators. particularly the students, Prokopi, and he said Paris, the Ponce, and Parrish. That's part. Perimeter, and with only classical. Okay, so this will show up shortly, maybe, hopefully in the next couple of weeks. But if you want to know more about the subject, there's essentially these two papers are some earlier attempts of what we're trying to do, and I'll show you essentially what we understand. So, just some context. I think I don't really need to say much about this here. I think most people in the audience are interested in matrix models, and well, we sort of understand that there's some, at least a class of matrix theories are supposed to be non-perturbative definitions of at least some theories of quantum gravity. So the example that usually people talk about is ADS CFT. So if you take n equals 4 superior mills in 4 dimensions, we really believe that this is the one-to type to be string theory on ADS hypothesis 5. But better than just saying that this gives a definition for what quantum gravity is, you might hope that there's an independent definition of what quantum gravity is, and that these dualities are really giving you two different descriptions of the same pieces. And if you're really lucky, like n equals 4, you have various parameters that you can mess with. And maybe you can reach some corners of the theory where you can actually have a controlled expansion, essentially. So, for example, I think we heard about this in the last couple of days. If you take planar n equals 4 superior mills, so by planar n equals 4 superior mills, I mean you look at the top. What is this one? Is there a,
I think it works on that screen. And
we'll just click the remote. So really by planar n equals 4, I mean you really take n to infinity and you keep this tough coupling fixed somehow. And this is a parameter that you can tune. So if you make lambda very small, you end up in a situation where you have a textbook QFT essentially. It's a planar gauge theory. Never mind. And really infinite coupling, you're supposed to get some kind of effective supergravity theory. And if you really believe this, there should be some kind of controlled high derivative expansion. But better yet, for this theory, really finite coupling in this really planar limit, we have something that controls the theory. There's some integral structures, it's a string signal model, and this is what really has been behind the great success studying n equals 4 superior mills. So at least in this regime, I think the theory is very well understood. But this is really not the regime where you want to do gravity, because taking n to infinity really just throws away all of the interactions. And if you really want to see interesting non-perturbative quantum effects, you really have to look at essentially operators or correlation functions where the dimensions of operators participating in the correlator scale with n. So this is, we heard about this yesterday from Anton. And in general, if you ask me, well, go and do this calculation. I picked some kind of generic operator and then try to go and do some perturbative computation. And what you find is that this is essentially all this. The theory is really, if you pick really the generic operator, you land in some chaotic theory, and there's no hope that you could ever do it. And well, the fact that you're losing control of this gauge coupling is telling you that, well, on the gravity side, the real degrees of freedom are not just strings. The strings are some kind of low-lying expectations, and when you start to look at very heavy things, you start to get very complicated downstream. Like that. So a more realistic one is, well, we can't solve this theory. This is likely chaotic, and it's going to be as complicated as QCD and generic But we still have supersymmetry, so some observables really don't depend on the coupling. So I think we heard about some of these on Monday. So for example, 3-point functions of half BPS operators don't get corrected. So in some sense, it's trivial, but because they're trivial with respect to the gauge coupling, you can really control the independence. So this is what I'm going to be talking about. So I'm going to talk about correlation functions where I don't have to worry about the gauge coupling, but have full control over n. So any questions? So some background. So what do I mean by n equals 4 superdiagonals? I'm not going to be talking about the whole theory. So if you're not an expert, what you can think of is, well, you have some kind of matrix quantum mechanics on R process 3 that you get by doing some KK reduction. I work in the weakly coupled limit, or you can just take the free theory if you like. So this is a theory of very many raising and lowering operators for each angular loop. And just because we're looking at half BPS operators, these are scalar, so I can just take the lowest one. So these have dimension equal to the charge, and this is independent of couple. And then the main problem is that once you step away from the planar limit, you have to be careful with the operators that you choose. So usually we take single trace operators, gauge invariant, but these are not orthogonal. So one approach is, well, okay, you start with a theory of finite n, and you find some orthogonal bases. So this is what Antal, Corley, and Sanjay did. So for one matrix model, you can do this very explicitly. This is a very pretty solution. For multi-matrix models, it's more complicated. But in practice, this is too much. Like you really, because I'm going to be working at large n, but not infinite, I don't really care that the states are orthogonal. I really only care that they're approximately orthogonal. So let's say that there's some kind of class of states that depend on some parameter, and for different parameters, their overlap is going to be basically non-perturbatively suppressed. So this is some kind of semi-classical state. Okay. So some examples of these things are, well, essentially there's 3 kinds of things that you can look at that are nice. The first are what we call exponential operators, which are essentially coherent states where you take essentially a potential, a polynomial potential in single operators. There's of course orthogonal basis. So this is a character over some representation. And something that came out more recently were these BPS coherent states that we've been working with data. And but the only ones that are really proper primary operators are the characters, because they have a definite dimension. And these other ones really have they only have sort of average dimension that's large. They don't have a definite conformal dimension. But this is not a bug. This is something that we actually. And things I will study today are 3-point functions. So supersymmetry essentially fixes the 3-point function of 3 half BPS operators to get this form. So this f is a kinematic function, which is fully determined by superconformal symmetry. And you have a lot of freedom to essentially just eliminate this. And some over OP coefficients. So these 3-point functions are not going to be honest OP coefficients. They're really going to be linear combinations, but that's okay. They're still valid observables. And today, just to keep it simple, I will talk about the case where 2 of these operators are sort of heavy in some appropriate sense. And the third operator, we'll see. Yeah. So the main trick is that I really don't want to deal with major quantum. Doing major quantum mechanics is a bit tricky, especially because you have to work with normal ordered operators. So instead, you can reduce the problem to just regular matrix integral. So people have been doing this since forever for 2-point functions. But for 3-point functions, you might be worried because of this normal order. Like if I take a naive matrix model like this, and I plug in 3 operators, in principle, this doesn't compute the same combinatorics because when you do this Gaussian integral, there's sort of weight contractions between each of these operators. But just happens luckily that for these N BPS operators, so they're parameterized by some kind of R symmetry polarization. So this polarization is null. So all the weight contractions between, for example, O1 cancel among themselves. So in this sort of description, it's very clear that you're only summing over weight contractions between sort of different operators. And I'm using operators kind of loosely here. It's really just integrals. Okay. And then you can use conformal symmetry to fix variables as you like. So, for example, the first operator I can call C. Second operator I can call C bar. And in general, I only have freedom to fix the third one to something. Where this Q is in phase factor. And then you just integrate out all the matrices that you don't care about. So you integrate out by 2, 3, and 4. And you end up with a matrix model, some complex matrix model, where you're computing some correlation function of this object that I call Q of O3. So this thing we call the Q transform. And really, all this is doing is normal ordering this quantity.
So can I just check? So what was the original model you started with? So you did want to take the matrix.
So basically, you can think of as matrix quantum mechanics of a complex matrix. Really, it's 6 real matrices.
And what's the potential?
It's just quadratic. So you first look at the free theory. You really it's n equals 4 span L set.
So you quadratic or quarter?
So let's just say the free theory. So it's quadratic.
Oh, I see.
But there's no quadratic term. There's no mass term.
There's a mass term on the sphere.
On the sphere.
Yes. So this is legitimately quantum mechanics. You do Lorentzian CFT, not infinity.
So you start from n plus 4 spring, so r plus this is 3.
Yes.
And then you end up with this integral.
Yes. So the claim is that this has the same combinatorics. I can derive this exactly from the matrix quantum mechanics, but I won't do that.
So this is some reduction of the BNN model. If I go into our process,
not quite. It's really, if you want to do this honestly, you're looking at a correlator in this matrix quantum mechanics. You introduce some generating function, and then you do all the weight contractions, and you end up with a matrix model for this generating function. So these are not the fields of the theory. These are some other things. It just happens that this has the right combinatorics. It gives you the same answer.
this is the combinatorics of just 2 complex fields and with contractions of complicated operators.
So these are not operators, these are matrices.
Matrices, yeah.
So these are n by n complex matrices.
What happens if you don't have the fundamental operator if you don't have phi1?
You have to. Yeah, well, okay. So if you don't have the component of the phi1, you're kind of in this extremal regime, and then everything just reduces to 2-point functions. So there won't be any weight contractions. Say you make it a function of C. There's no weight contractions between 1 and 3. So it's really a 2-point function. Yeah, you can sort of convince yourself that if you look at the remaining symmetry of these two operators, this is all you can do.
So if you are in the case,
If you're in the extremal case, you land in a very simple matrix model. I'll show you what happens when you get to different functions.
And you are ignoring phi1, or I didn't understand, or you are just,
I'm not ignoring it. So this phi1 is hiding in this Q.
but you are not integrating on it.
I will. So
Or this object is a functional of phi1.
So this object is a functional after you of C and C bar after you integrate phi1. And the process of integrating this phi1 defines this Q transfer.
Okay, so,
So-
phi1 is integrated to get Q. Okay.
Yes. So that's the important part. So these are, so if I start with some operator O hat 1, that's some kind of polynomial in C, this O1 is really the same polynomial with scalar matrices. But this Q is not. So the definition of this Q for some generic function is this. And well, if you do a couple of combinatorics, you see that this is really just subtracting off subcontractions. So just to give you some intuition, if you take n equals 1 and you take f to be a monomial, this is a generating function for permanent polynomials. So these are normal ordered things. For general n, you get some kind of Slater determinant of permanent polynomials. Okay, so let's take things very slow. So let's ignore the third operator for a second and just look at 2 points. So this is well studied. This is just so that everyone is on the same page. So my claim is that that 2-point function reduces to this moment in a Geneva type ensemble. So this goes back to the over Geneva. If you have a complex matrix model, you can't diagonalize, but you can upper triangularize. And for things that are holomorphic, this upper triangular parts really don't contribute to anything. So you get something very simple. And it's been known since forever how to solve these kinds of problems. So in the larger limit, you get some kind of a functional integral with the density of eigenvalues with some action, which is this. So this is just replacing the traits by an integral. This is the random ones. And then the saddle point equations for this are just that. So this log term will give you the inverse of the Laplace operator. So the inverse Laplace on the density equals this. So this is holomorphic. So when you apply the Laplace operator, these are killed. This is 1. So you get that the density has to be constant. But this only works if the density is not 0. So this density has some kind of distributional support that's constant in some regions. And the problem is, well, so if you're given these potentials, how do you find these regions? So it's a kind of moment problem. And just because this will show up, this data is exactly what you need to define how BPS solution detectors. So these are the well-known linear analysis geometries. And as long as the operators that we choose have average conformal dimension that is big enough, then you can trust this analysis. This density will be smooth enough and everything's great. And in the cases that we'll talk about today, the third operator is going to be small enough to not really modify this density. So let's compute some distributions. So the simplest one, this is well known to a lot of people. So this is the easiest one to find the density for, because you can just do the integration with the angular variables. You get this integral, and the saddle point tells you that essentially the radii are associated to these labels of the top. So what you find is you get these concentric rings. Okay, that's they're well known. So exponential operators are also well known. So this is what you find in the context of what's called a passive growth. So these, if you put a potential, you're deforming some kind of droplet, and this will develop these kind of tentacles. you take, for example, cubic potential, depending on the parameters, you find things like this, and eventually they have some kind of criticality. So the point is, it's very straightforward. You give me a potential, I can give you shapes. The ones that are not so straightforward are the coherent states. Because now the potential is not really a single trace, it's some complicated determinant. And if you're very naive, like I was before, you'd say, well, so these are coherent states. If you apply any function of the lowering operators to the quantum state, you get some function with the coherent state parameter. So you would just say, well, maybe the value density of the CI is the same as whatever I put it. I have these coherent state parameters and I tune them to be some distribution, and maybe they just follow. But it's not true, because like we saw, the density has to be constant. It has to satisfy this Laplace equation. So instead, you have the integral of any function over the density has to equal to what you get from the coherent state, which is some kind of sum over individual terms. So you can, in terms of looking, like we looked hard on how to solve this problem, and it turns out that it's solved. Basically, and Newton was already solving this problem. So these are called domains of quadrature. So it's a very nice classical solution to this problem. Essentially, what happens is, well, this is a sum over finite points. So if you formally turn this into a contour integral over the boundary T, you get some residues at these points. So there's Schwartz map, some residues inside the domain, and then everything else. It's just analytic. So you get some problem for this conformal map from the disk to some shape that you can solve. So this is, again, straightforward to do. So if I take this matrix to have two eigenvalues, say alpha 1 and alpha 2, with some multiplicity p, and the other one has multiplicity n minus p. So the density will look like this. So if they're close, it's essentially a disk. Then as you start separating them, it's like two disks that are very close, and they will not move until you reach the critical separation where you can't touch anymore and separate. This is to say that we have full control. If you give me any shape that you want to have, essentially you have a bunch of different choices to make it happen. So these quadrature domains are dense. So read any shape that you want, like in a construct, except that, well, the shape is not unique. So somehow you should pick the shape that has the maximal action in this function. So okay, what happens in gravity? So this sector is basically it's the simplest sector you could have. It's just one matrix essentially. So the dual theory of gravity has to be equal to 7. And in this case, the theory of gravity is essentially the theory of one scalar function. So the whole metric is determined in terms of this function, which is harmonic. So the linearized perturbations on top of the theory are really just governed by deformations of the scalar. So this is really the killer potential for the metric. Never mind that. And well, the expectation values of operators really just correspond to the asymptotic values of the expansion of this function. So this was known from the work of Skinners and Taylor. So again, I'm making it sound very easy, but in practice, this was really a very difficult computation. And the main difficulty is that these geometries are not products. They're not ADS 5 times something. They're truly 10-dimensional geometries with non-trivial topologies. So the naive thing that we do is you would try to expand around infinity and do some kind of Kaluza line reduction, but this has to be nonlinear. So it's, again, they really worked hard. They had a series of about 3 or 4 papers with really, really, really good work. And the result is this. So you can, when I compute it up to basically 1-point functions of operators, single trace operators, of dimension of up to 4, and you get these nice formulas. And as far as I can tell, this is as far as we know from gravity. If you try to go higher than this, it really seems to get quite difficult. You need to do, I think, the nonlinear KK reduction to cubic and so on order. So it's really quite non-trivial. So if you just, I guess if you were doing this calculation back in the day, you would be really happy enough to have this, and you would not really stare at these polynomials for long. But I kind of had to stare at these for a long time, so I ask you, do you see a pattern here in these polynomials? And the answer should be no, not really. So the reason that you don't see the pattern is because these are not the right things to look at. The right things to look at were these operators where had these Q's. So these other things were the coefficients of the expectation values of these guys. So what we can do is we can define this kind of reduced operators on the eigenvalue ensemble, basically by integrating out the triangular matrices, integrating out psi 1. And then we just get some kind of n-dimensional integral, which is approximated by the test. So the job was, well, let's look at what these things look like. So I worked a bit hard with some weak contractions. I got this. And what you find, you've been staring at this for a couple of weeks as well, but the first one is strict x. The second one is strict x squared minus 1. The third one is x cubed minus 3x. This one is x to the 4 minus, this one's a bit weird. X to the 4 minus 4x squared plus. From the first three, it kind of jumps at you that they're just Fermat polynomials, which should make sense because I've been just normal ordering. So Fermat polynomials, all they do is just normal order. Starting at dimension 4, it gets a bit more complicated. You get sort of linear combinations of Fermats because, and this is nice because there's non-planar contributions to these things actually. Which you might be confused about, but there's some kind of extremal coupling enhancements. And the reason that the Skanderson-Taylor computation was so complicated was exactly because they had to work really hard to get these extremal couplings. Otherwise, I would just get these Fermat polynomials. Okay, so I did this by hand up to 4, but we have better ways of generating these. Essentially, as far as you want, I can just plug it in mathematically. Just give you the polynomials. Okay, so that is all sort of very simple. If you've been working on this, you kind of knew all this. It's just now very kind of clean. So now I'm going to do something that we didn't know. So the next kind of natural thing that you can do is, okay, you can look at expectation values of single traces. So what if you look at expectation values of something bigger, like a determinant or a subdeterminant? And what we'll care about is, well, the regime where the dimension of this third operator is of order n. So that the dual description is and just for a second, I'm going to restrict the characters for the background space. But hopefully you'll see it's really not important, just to make things simple. And okay, to be extra pedantic, instead of working with these characters, which are tedious, I'm just going to work with a generative function. So, okay. So actually, how should you compute this normal ordering is, okay, we integrate over this phi 1 field. This determinant, you can write as a Gaussian integral over some auxiliary fermatic fields. So it's a Gaussian integral, you can do this. That's not really too bad. What's bad is when you do this over triangularization. So naively, you'd think that you have this matrix M that you want to diagonalize it, that you want its eigenvalues, but you really want the eigenvalues of C and C bar, the eigenvalues of C plus C bar. So you really get this kind of upper triangular integrals with linear terms in T and T dagger, which are not so nice. So now you get something that is not clearly kind of H invariant. And well, importantly, these M's are not eigenvalues of that. So, and then what you do is, well, you get this kind of mess with fermions, which after some work you can actually just rewrite in terms of fractal integrals. So basically the final answer is that you look at the normal order version of this, you reduce it down to this eigenvalue matrix model, you get these Hermite polynomials, as you would expect, some kind of determinant. So okay, you get an integral, and you can do this integral. So it gives you some determinant, and these HI are related to the. Let me draw a picture. It will make more sense. So if I have a Young diagram, this is something like that. So things not very complicated. This HI are really just reading it the wrong way. So you start at the bottom, and then you count backwards. So it's n minus I plus 1 plus R and so on. So what this does is it adds some kind of linear diagram. Okay, so this is a tri-diagonal matrix. So what you will notice is if these are diagonal terms are 0, then it factorizes. So you will get some kind of block structure, and it factorizes precisely when essentially the length of the rows of the Young diagram shift. So if I have some kind of thing like this, this will lead to determinants. So if I can solve the problem for one block, I solve it. So let's solve it for one block. So in general, it will look like this. You play around with it for a bit, and you see that it satisfies the recursion part. And if you work with matrix models, you should be kind of screaming at me because this is really obvious, right? This determinant was really it's really some kind of Henkel determinant. These determinants for various values of fan are just orthogonal polynomials. They're really, when people were looking at matrix models back in the days, you look at the correlators of density operator and these other things that you find. So for this case, with these characters, the orthogonal polynomials are just happen to be known. They're associated Hermite polynomials. Okay, so you integrate, and this is what you get. So, okay, I worked very hard. Basically, I did a bunch of acrobatics, and I landed with some binomial coefficients. So you were like, okay, well, why would you do that? This was a counting problem. Why did you do all that? But then you stare at it for about a week or so. So, okay, for a single block, the density of eigenvalues the ring, where these edges are these edges. So if this is A, this is B, A squared is like, I think, and well, it's the length. And B squared is going to be the length plus n. So, okay, you use Stirling's formula, you get rid of n and k in terms of this more geometric variables, and you play around with integrals, and you find that this asymptotics are just this. So it's some exponential or some integral, where the endpoint of this depends on the dimension of the operator that you're probing with, and this is where all the dependence in the background is. And this is very suggestive of some kind of saddle point approximation, because it sort of is. So in the larger limit, these polynomials will have some kind of WKB approximation. Okay. And in general, so we solve second-order differential equations, so we'll have two terms. You can check that they differ by a sign. That's not important. And after you work, what you find is that what the momentum function that you find here for the WKB approximation is the resultant. So it's really just it's an integral of the distribution of the eigenvalues. So really, this is just a function like this. So if you stare at that's what that comes from essentially. And the other term is the same for the Hermite polynomial. Let's see what else we make. Yeah, so just so that you see what happens, you pick some values of parameters like I think this is n equals 20, the length equals 10, the dimension is 16, and then you plug in this function that you integrate, we get this solid line, and then this red line is the asymptotics. So it doesn't look so good. And then you might complain to me that, okay, how did you fit that? Like, you really only found the exponent. You didn't find the pre-exponent. How did you fit this thing? Like, you're not told that from the Hartnoll approximation. Well, because I'm looking at the log. So the actual functions don't really agree, but you find that the logs are really, really close. So the saddle point is really not telling you the right answer, but it's telling you the right asymptotics. I think I checked for this case with n equals 20. You get up to like 1% accuracy, even though you're not doing the right thing. Okay. So this is peculiar. These OP coefficients go with n, sort of exponentially. So this is telling you that this is some kind of D3 brain. Like the tension of D3 brain is n and ADS units. So this looks like the action of a D3 brain. And the way that I interpret this is you're taking some kind of overlap of two wave functions. So the first wave function is kind of like the bulk wave function. So this background has some kind of expansion in terms of instantons. So if you work with matrix models, you would call this some kind of FCCT, right? So it's an eigenvalue instanton. And the other wave function is just the function of your probe. So you're just projecting that to whatever you want to probe. So if you worked on this is what we really naively thought at the beginning. This wave function should be just the integral of the result, which is what the asymptotic seems to tell you. But so okay, you go and look at the literature, you find these kinds of formulas everywhere, and they tell you, okay, so this wave function really is just giving you the effective potential for an eigenvalue. But that's only valid if the eigenvalue is outside the distribution. In our case, most of the integral really comes from the distribution itself. So it comes from the oscillatory region of the wave function. So again, you look at these parameters, you look at the density, and you look at the integral, and it's mostly all inside. And this is like 10 to the minus 20. So really what you're probing is some kind of instanton contribution to the charge. Okay, so that's a bit confusing because at least if you follow the first part of the story, you would just think that you take this density and then you plug in the saddle point for that density and then you get some kind of nice answer. But this is telling you, no, not really. These kind of operators know way more than you think. So at finite n, when you try to solve these saddle equations, you find many saddles. You don't just find this distribution. And when you do this kind of like steepest descent decomposition, the other cells that you find are basically where you tunnel out some eigenvalues. If you stare at this formula, it looks like this is like you tunneled out some radius, which is going to look like this. And you can check that for all values of delta, this radius is inside that distribution. So it really seems to be a hole. Okay. And again, this is very different from what you see with single trace operators. With single traces, you only see the smooth saddle. With these, you seem to see a lot more. Okay. So as a summary, so these protected correlators carry a lot of non-trivial information. I showed you essentially how to compute the simplest things in any background and how to prepare any background. And these correlation functions agree exactly with what you get from supergravity. I gave you some formulas for some exact correlators with some heavy probes, so these are new. And I would expect that these describe some kind of Instanton effects on the string theory side. The large limit suggests that there's a saddle point. We still haven't completely controlled the saddle point because, again, this is the regime where you're inside the cut. So the function is not analytic, and you have to work a lot harder. But I think it's doable. I think we're just doing things not quite right. Okay. So the takeaway, I like this BPS coherence space. You can make any background with them essentially. And I didn't tell you this, but there's a similar story for less supersymmetric states. Seems to be qualitatively similar, except that we don't know how to reduce to eigenvalues in that case. If we knew how to reduce to eigenvalues in some sense, so the eigenvalues of commuted matrices, you would get some kind of problem with quadrature domains in higher dimensions. Maybe there you could attack the problem. But it seems very complicated. It seems to be related to legitimately difficult PDEs, like Modularity type equations. So it would be nice to see these kind of Modularity pair equations show up from matrix. I only showed you the simplest things that we can do. I don't have time to show you the whole thing. In practice, we computed some correlation functions, at least some saddle point contributions to correlators with 3 really heavy operators. And by computer, I mean really analytically found the density of eigenvalues. I don't know what to make of these in terms of gravity. And well, this is, I think, evidence that large NCP angles really make sense, at least in some semi-classical corners for these BPS operators. And you might be able to do controllable, sort of efficient calculations in the theory. So one thing would be to try to break this to perturbative calculations, which I don't think is really that hard. And really, I think behind all this really nice story with this protected operators is some kind of topological string theory hiding. There's been some progress on this. So very well, I could have just talked about the paralogical subsector of the theory. Nothing would change. The gravity theory would not really change. It's still essentially a free boson. Except that there, everything is presumably well defined. I don't have to care about whether things are protected or not. They're always protected. So maybe that, looking back at this topological string literature, like topological vertex, that might give some intuition of what's going on with these heavy operators. And I think that's all I have. Yeah.
Thank you for the introduction, and thank you very much for the invitation and for giving me a wonderful opportunity to talk about my work here. So today, I would like to, well, of course, talk about the matrix model, but probably the main result in this talk would be about perturbative string theory. And you may think that perturbative string theory is well established and it's kind of boring, but I'm going to talk about something very new in the Minkowski signature. So in the Euclidean signature, everything is, well, well understood. But in the Minkowski signature, there are some subtleties. So I would like to explain about it. Okay, so, well, we usually start with the non-Goto type action in the Minkowskian space, for example, in the textbook for string theory. And at some point, we somehow recroated the theory to the Euclidean signature. And we used the polarised type action, which is classically equivalent to non-Goto type action. So this matrix is well defined by this path integral. So by calculating this path integral, we can compute scattering amplitude in string theory. But we use Euclidean Polyakov type action of string theory. And well, the thing in this thing is this is just perturbative expansion. So this it's expansion in terms of GS, G string. So we need non-perturbative formulation to define string theory in a healthy way. So here comes the matrix model. So there are some matrix models which is considered to describe string theory non-perturbative. So C equals 1 matrix model, BFSS matrix model, and IKKT matrix model, and so on. And one simplest example is 1 matrix model, which is written in this way, and you can compute correlators, which is written by the matrix size n and coupling lambda. So by taking the double scale limit, keeping this particular combination of couplings and matrix size n, we can get a function of G string. So there are some study in this model, and it is known that this model describes 2D pure gravity for one-dimensional particle. But in this talk, I would like to talk about the IKKT matrix model. Okay, so the IKKT matrix model, which has been already explained well. So I'm gonna go through just briefly. So this zero-dimensional theory is considered to describe type 2B superstring theory. And there are nice features. For example, it has supersymmetry identical to type 2B superstring. And of course, as shown explained, there is a gauge gravity picture in the matrix model. And it also produces perturbative results like graviton exchange potential and the brane scattering amplitudes. And there are some study about string field theory. To my best understanding, this hasn't been established in a satisfactory sense, but at least free string field theory can be reproduced from the IKKT matrix model. And more importantly, there is a possibility to realize 3+1 dimensional spacetime taking the margin limit. So there are nice features in the IKKT matrix model. But here's the problem. So the theory is zero-dimensional. Now, how do we define the theory? Well, in usual quantum field theory, we have time. So we can start with the Hamiltonian, and we can just, derive the path integral from the Hamiltonian formula. But in the IKKT matrix model, it's zero-dimensional without time. So we don't, in principle, we don't have any access to the, any reasonable reason to consider path integral. But it's in standard QFT, it's natural to consider the theory as the theory quantized by the path integral formalism. So this partition function could be one of a natural way to define the theory in the Minkowski signature. So I I introduced G mu nu here, which is the target space metric. So if we choose the Minkowski metric eta as G mu nu, then okay, so we can define the theory in this way by using the weight as exponential IS. But there are many choices, right? Because we have we can have exponential minus S instead, and we also we can also consider G mu nu equals to just the Euclidean metric. So roughly speaking, well, in this from this point of view, we have four possible definitions of the IKKT matrix model in path into formulation. And conventionally, we call this Euclidean type as the just the Euclidean IKKT matrix model, and this one Lorentzian as the Minkowski matrix model. So from the first principle, it's impossible to determine which one is the right one to define the theory. So we will try to answer this question by, well, revisiting perturbative string theory. Perturbative string theory is, well, it's written, as I explained, it's written by Euclidean Polyakov type action like this. So now the questions. Well, is it equivalent to the Minkowskian theory? Because we consider the Euclidean theory, it's well defined, but in the Minkowskian theory, we have exponential IS, so it's not absolutely divergent usually. So it's not trivial to say it's equivalent to the Minkowskian theory. And also, we have the Polyakov type action here, but still it's non-trivial to say it's equivalent to Nam-Goto type theory. And especially for a Minkowskian Nam-Goto type theory, we have square root here in the exponent. So we need to pick up a branch to define the exponential, to define the action properly. So which branch should be chosen in the theory? And finally, we would like to reproduce QFT in the Minkowskian signature. So we expect something like causality, of course. So let me elaborate these questions a little bit more. The first one is about Euclidean versus Minkowski. So people may think that, well, we can just rotate it, but it's usually not possible to equate two theories. So, okay, so let me explain that one briefly. If we naively rotate the theory like this, so we have x naught, and well, it's rotated to xt with this rotational factor exponential minus I theta, and theta goes from 0 to pi over 2. And we also have, well, this is the Polyakov type theory, so we also have Zweibein. So we can rotate the Zweibein in this way. So we should obtain something like this by plugging these into the action. So we have these factors. So the basic way to equate these theories is using Cauchy's integral theorem. So if we consider a path, a contour like this, then this integration over this on this real axis should be equivalent to the imaginary, well, integration over the imaginary axis if this dashed line integration over the dashed curve vanishes in the limit. So in order to make it possible, the exponent in the path integral should be negative definite in the real part during the rotation. So looking at this, we have expression minus I theta, which is negative definite during this rotation. And the second one is okay. The final one is okay, but the third one, this is positive definite. So by this naive rotation, we cannot equate the Euclidean theory and the Minkowskian theory. Okay, the next one, Navigator type and Polyakov type. So I write Navigator type and Polyakov type and shift type action in this way. H is the determinant of the induced metric. So I use HAB throughout this talk. This is the induced metric, and H is the determinant of it. And yeah, the shift type, this is also equivalent to the Navigator type or Polyakov type action classically, which should be familiar to those who have worked on the IKKT matrix model, but probably it's not so familiar to some of you. Well, I will review the equivalence of these three theories classically first. But yeah, this equivalence is kind of very easy to show classically, but quantum mechanically, it's not trivial. So I'm going to explain this as well. Final one is about causality in string theory. So causality in standard QFT is realized by the I-epsilon prescription and also the existence of antiparticles. And we usually say that the commutator of fields at different points for space-like separation, it should vanish, so that the observation at each point are independent if they are, separated space-like way. But this cannot be, it's non-trivial to say this type of statement in string theory. So especially in protective string theory. So if we consider SFT's string field theory, then there are some discussion about it. But in protective string theory, it's difficult to say something in this context. And it has been discussed by Witten in 2013. And before Witten, there are some discussions about the causality in protective string theory, but it's not well understood yet. So then what do? We naively expect causality can be realized in string theory as, that space-like propagation should be prohibited in string theory. So for example, if we have, the up direction is the time direction, and if we consider two strings like this, and so this bridge propagation is space-like in this figure. So this kind of in this kind of propagation, the area of the worldsheet should be positive. The area should be negative in string theory. So if it is space-like propagation, then determinant H is positive in this around this area. So this should be prohibited in the sense that, if you expect causality is realized in string theory. So this is a naive expectation in string theory. And I would like to explain this kind of structure is it's already there in string theory in the Minkowski signature. Okay, so back to the questions. The first one is it equivalent to the Minkowskian theory? Well, I'd like to answer this question as yes. And the Navigator type formulation, yes, it's equivalent to the Navigator type formulation. And for the Minkowskian Navigator type formulation, the branch should be selected by I-epsilon terms, which appears naturally in the computation. And about causality, as I explained, the naive expectation should be is realized. I'm going to explain this later. Okay, so after this point, I have done the introductory part. So, do you have any questions so far? All right. So I would like to briefly review the classical equivalence first. Okay, so this is the table. I guess it's better to explain how we, where do we go in this talk. So I'm going to explain the classical equivalence first. So it's just a review. So I'm going to do this briefly, and then I will explain the quantum equivalence.
Just to go back, I think my concentration lapsed slightly.
All right. Yeah, it's late. So yeah.
When you said the equivalence to the Minkowski theory, are you saying to the matrix model?
No, it's about perturbative string theory.
You're just perturbative string theory is equivalent to perturbative Minkowski formulation, perturbative formulation in the. Can you go back one second?
Sure.
The perturbative in the Minkowski theory, yeah, that's fine. But and in the Navigato, but when you sum over genus in the Minkowski theory, how do you deal with the fact that you don't have a causal structure, or where there are certain points where the metric has to be 0 in the Minkowski setting, which is not true in the Euclidean?
Well, yeah. Well, basically, it's about the Polyakov type.
Right.
It's about the Polyakov type action. In the Polyakov type action, we have worldsheet metric. So
the Polyakov one has no problem. That's Euclidean, and the Euclidean metric has no problem. But the
Minkowski, yes,
metric on the worldsheet, it has to be 0 at some points.
Yeah, there should be some singular point in Minkowski theory, but I would say, well, there wouldn't be a problem because, well, a classical solution to the Minkowskian string theory has always, well, not always, but it usually has cusps in the integration. So I would say such kind of similarity doesn't cause any problem. Well, I'm not sure about it, but
higher genus, so just
higher genus, yeah. But in this work, we haven't worked on that kind of, higher genus computation or such things. So I cannot say something firm about it. But there are many things which is not understood in this course of work. So
If I'm not mistaken, when you like constraint for theory, that's exactly where vertices lie. So shell everywhere, and then the similarities, so we do the things. And apparently, open string field theory does provide a triangulation. That's basically the strings. And therefore,
open string theory should be okay.
Yeah, that I don't know the constraint works out.
If you think of a high function, which is just appropriating time, you've got.
Yeah, this is why live code kind of works. Yeah, but I would claim that probably something like that has to work out.
Thank you. Okay, so if you don't have any questions, I was talking about how we go in the talk. So I will explain the quantum equivalence then, and after that, well, up to this point, it's about the perturbative string theory. So after the discussion about the perturbative string theory, I'm going to explain how we obtain the matrix model from the perturbative string theory, which is essentially done by Hikaru Kawai and his collaborators in the IKKT paper. So there is nothing difficult in the equation part, but I'm going to explain what we can obtain from this point of view. Okay, so I'd like to review how the Navigato type and Polyakov type and Schur type equation formulations are equivalent in the classical context. So we start with so this is the Navigato type action with in the Green-Schwarz formalism. So we have something like Feldman term for the so-called Chern-Simon term here. And this is the area of the worldsheet. And there are two kinds of Majorana biofermions we call theta 1 and theta 2. And it has the induced metric is written by a supersymmetric invariant, super embedding pi. And this pi is invariant under this symmetry. And we also have kappa symmetry so that we have a proper number of fermions in theory. So this Namagoto type action, it has constraints in the theory because it has gauge symmetry. So we have diffeomorphism and kappa symmetry. So we have these kinds of constraints. So we can compute the Hamiltonian by using constraints, by using the Lagrange multipliers. So the Hamiltonian is written like this, without only with the constraints, because the Hamiltonian is 0 if we don't introduce these terms. Then we Legendre transform this theory back to the Lagrangian formalism. Then we get the Polyakov type action like this. And this worldsheet metric is written by lambda naught and lambda 1 in this way. Okay, then then the shield type action can be obtained from this Polyakov type action by integrating out lambda 1. So this area part is written in this way, and lambda 1 appears only here. So we can classically integrate out lambda 1 to obtain shield type action. So it's just easy to get this action by from this type action. And here I change variables from lambda naught to EG. So EG is just an auxiliary variable. And then integrating out EG again, we obtain the Namagoto type action. So this is the classical equivalence between these three formations. Okay, so now let's move on to the quantum equivalence. So this is overview of the quantum equivalence. So we are interested in this type of pattern as well. But okay, so we mainly work on the partition function in this talk. So the starting point is Polyakov's Euclidean path integral, like this. And then I would like to explain how this is equivalent to the Minkowski path integral with the Polyakov type action. And then, I will explain how this is equivalent to the Shields type and Namagoto type formulation. And a caveat is that the equivalence holds for critical string theory. So it's not critical, then the equivalence between the Polyakov and these two breaks down. But generally breaks down. So critical string theory is an essential part in this equivalence. And I have shown the equivalence for critical type 2b, type 2a, and critical bosons, but in this talk, we would like to focus on the bosonic part because that's the essential part in the equivalence. Okay, so this is the starting point, Polyakov's Euclidean path integral. Now we have the measure of the metric here. And the measure of the metric is defined in this way, in a standard way. So we have a standard norm of the worldsheet GAB. In this way, this is a very standard way to define the norm of the worldsheet metric. And from this, we can easily find out how the measure of the metric is written, and it's written in this way. Here, phi is the conformal factor, and we have lambda 1 and lambda 2, as I explained. So, okay, so this is the measure dg, and here the critical part, the criticalness plays a role, because if we consider critical string theory, then the integration over the conformal factor is trivial. So integration over d phi is just, it just gives a trivial number. So we can safely integrate out d phi, and we can then integrate out lambda 1 and lambda 2 to obtain Namagoto type action.
Sorry, can you just quickly ask, the norm you have there for the metric perturbation,
I mean, that's the norm, but there are other norms you can take, right? There's another, it's like this DeWitt metric.
Another one with conformal.
Yeah.
Yeah.
So that's what
Yeah.
usually gives the conformal factor problem for GR. Why do you, I mean, how do you know what you should take here?
Okay, that's fine. If you add such kind of term in the norm, it doesn't change the measure of the metric.
I see, but the conformal, the Weil factor would become negative. I think fluctuations in the Weil factor, it would change the sign of that last term, the delta phi squared. Could change the sign.
Yes.
Which maybe you don't mind if it decouples anyway.
Yeah, that's what I'm thinking. It decouples, so
I see. So maybe
yeah, that's what I'm thinking. Okay. If you are satisfied with that.
Yeah.
That's okay, so integration of a phi is just, well, okay, let's say trivial. And then we can integrate out this lambda one very easily because it's just a Gaussian integral. So we obtain the Schulz type action in this way. Okay, so then we move on. Okay, so this Schulz type action, it's written in this way. Well, here I change variables. Now we rotate it. So by using Cauchy's integral theory, we consider Wick rotation, and the Wick rotation is defined in this way. So this rotation is just the same as the one I explained before. And here we rotate the EG in this way. So in the Polyakov type action, we naively rotate the Vafa. But here we are considering Schulz type action. So we rotate something like volume factor. And theta goes from 0 to pi over 2. And okay, so yeah, we plug these into the path integral to obtain something like this. So this exponent is written in this way. And but note that this factor is just a determinant of H. So it's positive definite in the beginning, in the Euclidean signature. So by the Wick rotation, it's the exponent is negative definite in the real part. So we can safely Wick rotate the theory, Euclidean theory, to the Minkowski. So by taking theta to pi over 2, we get this one, which is the Minkowski type action. So this is the result. So we have Schulz type action here, and EG is integrated over from 0 to infinity. But this, okay.
Sorry, can I just ask one more question?
Right.
I mean, there's two things you need when you do the Wick rotation. One is that these extra arcs of infinity don't contribute.
Indeed.
But you also need there to be no poles in the complex
Exactly.
Which is probably a complicated question.
It's complicated, but yeah. So I assume that we don't have poles in the graph. In general, if we consider vertices in the path integral, there could be a pole, but we are not discussing that in this discussion. I mean, we are talking about path integral. It's just simple path integral. So in this case,
without insertions.
Exactly. So yeah, as I said, if we have vertices, then we need to care about it. So yeah, this is what we get. But this one is obtained by Wick rotating, varying theta from 0 to pi over 2. But we can Wick rotate in the opposite direction, from 0 to minus pi over 2. This integration gives integration over EG in the negative region. So we combine two of them to obtain integration over EG from minus infinity to plus infinity. So this is what we can get from starting with the Euclidean Polyakov action. And here we have Minkowski and Schulz action.
You added two contributions?
Yes, I had two contributions.
What is that?
To simplify this, because if we don't do that, EG goes from 0 to infinity. So it's just a trivial change of the expression. So they are just equivalent. If you want to write theory only by the positive EG, then that's fine. But it's equivalent. This. Okay. So
How do you avoid the singularity around EG equals 0?
EG equals 0. I'm assuming that we take the usual, the limit so that EG goes to 1. So this integral can be defined in a way that we avoid 0, right? EG equals 0 can be ignored in a sense. So by taking the limit, we can define the usual. So okay. So it has singularity EG, but this integration is convergent. So I don't think it's gonna cause any problem.
There is an essential singularity, the G equals 0, so
There is?
an essential singularity there.
Well, the measure has singularity, but integration is well defined.
Do you have a prescription as to which side you should push it away from 0?
Which side? What do you mean by which side?
I think you were saying that the question was associated with the singularity, the G equals 0, and you said you can avoid it. But that means you move it to one side of the, you drop some small circle around 0, presumably.
Yeah. What I think is just like well, I'm talking about something like this, so it's just simple definition to do something like
And
this.
the limit there as epsilon goes to 0 is not problematic.
No. And we can do that. We can do this integration properly. So, well, in the case of touch function. So this can be, okay, so what we have got is the shear type action. And the path to the Polyakov type action is very easy. It's just the other way around of this discussion. So we insert 1 equals to this integral. So we get the integration in this way by changing variables from EG to lambda naught. So this is what we get, the Polyakov type action. So up to this point, I have explained how Polyakov's Euclidean path integral is equivalent to the Minkowski version.
You don't worry about the fermions at all.
Fermions, you don't need to worry about it because, okay, so that's because the fermionic term doesn't contain this EG term. I mean, the worldsheet metric appears only in the area of the worldsheet part. So yeah, that's why the fermion doesn't contribute to this pattern. Well, yeah, well, actually, that's not the true answer to that question because we have fermions inside the induced metric because induced metric is written by super embeddings. So, well, if we don't fix kappa symmetry, then we have a problem relating to that fermionic part. But if we properly gauge fix kappa symmetry, then we can do the same thing. Yeah, in the same discussion is applicable. Well, I don't have time to explain that kind of technical thing. So yeah, I like to skip that part. You can ask me about that later. Yeah, after this talk. But yeah, you don't need to be careful, worried about the fermionic part. Okay, so yeah, okay, so this is how we get Minkowskian version. Now, this is the Minkowskian shield type path integral, but implicitly, we consider epsilon terms in the Minkowskian shield type action because we rotate the Euclidean theory to get the Minkowskian theory. So, by the weak rotation, we implicitly consider something like I epsilon. So, thing is like this: we have epsilon terms in this way. So, yeah, in this case, we start with the Euclidean type action, and we get naturally epsilon terms. But this epsilon terms is also natural in the sense of Minkowskian Polyakov type action, because epsilon terms can be regarded as terms coming from the ground state wave function. So we are interested in S matrix in string theory. So we usually consider insertion of vertices. So insertion of vertices usually mean that, well, implicitly means that we insert ground state wave function as well. So in that sense, epsilon terms naturally appear in the Polyakov type Minkowskian theory.
Sorry, can I just look? Where did this epsilon come from? It's not this epsilon, the regulator up here. It's a difference.
No, sorry.
It's nothing to do with that.
Nothing to do with that. Epsilon just comes from weak rotation. So it's just we have theta here. So if you set theta equals to pi over 2 minus epsilon, then you will have epsilon term. It's just that. So
I see. But you need it here? You
yes,
can't just set it to 0.
We can take the limit of epsilon equals to 0. But
it has to be there.
If you take
on
it,
how you take the limit, you get different answers.
The purpose of epsilon term here is just to define the theory in a healthy way. So if you are satisfied without epsilon, that's fine. But implicitly we consider epsilon term because without it, it's just conditional convergent. So this is for the purpose of the convergence.
I just mean normally in quantum field theory, you have to have I epsilon because the integrals simply don't make any sense without it.
Yeah.
But here you're saying the integral does exist without the I epsilon, or it doesn't exist.
Doesn't.
It doesn't.
I would say
It's the
doesn't.
same thing. Sorry.
If I do just a one-dimensional integral, it presumably doesn't exist without an I epsilon.
What do you mean by?
Just an ordinary integral with over EG. I think that's the same reason that you need an I epsilon. Just geologically.
Yeah, in the usual calculus, we implicitly consider something like epsilon term.
Exactly.
So in that sense, we may not need it, but that's a bit naive, I would say. So to avoid such kind of naiveness, I introduce epsilon to make it well defined. Okay, so we have regulators like this, and this plays an essential role to obtain causality feature.
This kind of epsilon becomes important when you calculate one root, right?
Yes,
For free level, this does appear. We are just a function. So,
right.
So how this is converted to epsilon of the propagator?
That point, I would like to address that point, but yeah, I'm working on that, but it hasn't been obtained yet. So my guess, my guess is that this epsilon is related to the usual standard QFT epsilon prescription, and I have already obtained something support that speculation, but I haven't proved it in a satisfactory way. So yeah, I would say this epsilon should be related to the usual QFT epsilon. but I'm not going to talk about that because I haven't proved it yet. So yeah. Okay, so this is the short type action. We just consider this part without dx because dx doesn't play a role from now on. So this is the path integral, and this integral can be done easily, and this is the result. So by integrating out EG, we get the non-Boto type form with this factor coming from the measure of EG. And this is the final result. So by putting two of them in a single expression, we obtain non-Boto type action. So we put these signs in the form of variable s. So s equals to plus minus 1. So non-Boto type action, if you define non-Boto type action with these signs, then this is equivalent to the Euclidean variable type action. So this is quantum mechanical equivalence between them. And
so do you need the epsilon display in your order in this calculation?
Yes, because without epsilon, it's difficult to, well, okay. Yeah, epsilon is sort of essential to obtain this. Yeah, actually, I first computed this by using Mathematica just for playing around. Then Mathematica gives some answers, but it doesn't care about epsilon, so it easily make mistake. So with epsilon, we don't make any mistakes. So yeah, this ensures this form. Sure. And the nice thing about this is looking at this middle expression, we can see that these two terms cancel if the determinant h is positive. So if determinant h is positive, then these two exponentials are just expression minus s, and this factor gives the opposite signs of this cancel. So by causality, I mean this. So the causality is realized by the existence of the second term. So if we interpret the first term as the fundamental string, then the second term should be anti-fundamental string. Because well, if we have B mu nu field, then the B field doesn't contain the worldsheet metric. So it's just a factor it just factorized to this path integral. So this sign is.
In what sense do you mean they cancel? I'm not quite sure.
Oh, sorry. So looking at this, we have if h is positive, then we have minus epsilon here. So we get minus I square root of h. Okay, so I'm going to write it. So we have exponential square root of minus I minus epsilon. And minus I, minus I here. And if h is positive, then this minus epsilon picks a branch. So it gives us minus square root of h. And the numerator, well, we have the denominator. So denominator gives minus I.
How is that summation working? Your summation sum over S of sigma equal to minus L plus 1.
Well, this is just a short notation of this term. So we have this one s equals 1.
Oh, but then the brackets in this thing, I see it.
Brackets. S of sigma, right?
Is that quantity totally real?
Sorry, what do you mean?
Is that whole right-hand side real? Is it of the form, z plus z bar?
Okay.
If it's not,
it should be real. Yeah, it should be real. Because we started with the Euclidean type actions, which should be real. So yes, so S equals 1, if we interpret S equals 1 contribution as fundamental string, then S equals -1 should be anti-fundamental string. So the causality is realized by the existence of this fundamental string. Now, this is sort of a weird thing, right? We have something like negative energy contribution because it looks traveling backward in time because of the sign in front of the action. But I would say this is not very weird because, well, in the first place, there is no one-sheet time direction because, you know, we have Hamiltonian only contains constraints. So H is 0, meaning that time evolution doesn't exist in a sense. So from that point of view, is traveling backward in time is not very weird. Yeah, from this time evolution sense. And another one is another explanation would be even if we have anti-string with positive G naught naught. So G naught naught should be negative usually, but even if we have positive, we can obtain a negative G naught naught only by changing sigma naught and sigma 1. By swapping sigma naught and sigma 1, we can just, you know, the right sign in a sense. So this kind of so since we have this kind of open closed string duality, I would say the traveling backward in time is not that weird in the path integration. So the conclusion is okay. So we can interpret this anti-F string in a sense. So my suggestion of this interpretation is, well, it could be negative energy anti-F string. So yeah, if we consider positive energy string for S equals 1, then we have S equals -1, which should be regarded as negative energy anti-string corresponding to positive energy string. Well, this hasn't been established, so it's just an interpretation of this phenomenon. But yeah, this may be related with anti-particle and particle interactivity. I'm not sure about it, but yes, this is one interpretation of this phenomenon.
What do you mean by negative energy?
Negative
particle and anti-particle both observe positive energy.
Yeah, in QFT.
Yeah.
Yeah. By negative energy, I mean this. We have exponential minus IKX. If K naught is positive, then it can be regarded as negative energy. So it's kind of Fermi interpretation. So yeah, this terminology doesn't is not that important. It's just a way of describing the object. Okay, so yeah, the interpretation is not very clear, but yeah. Anyway, the interpretation is maybe not clear, but what we got is the cancellation. So that is from result. And I would like to use that to discuss the matrix model. Okay, so for the non-partitive definition, we in order to get the matrix model, we matrix realize the theory. So yeah, by matrix realization, we expect that the matrices describe multi-body systems of superstrings with various genera in this way. So by matrix realization, we consider that we get non-partitive formulation. So that's the idea. And by doing matrix realization, well, is just a map from function to a matrix. And yes, the matrix, well, in order to get the matrix regularized theory in the Short-cut theory, there would be two ways to regularize theory. So one way is after the weak rotation. So since we have seen that Cauchy's theorem equates the Euclidean theory and Minkowskian theory, we can safely recrotate the theory to the Euclidean version. So after we get the Euclidean version, we can just apply the matrix realization to get the matrix model. So that is one way to obtain the matrix model, and that leads us to the Euclidean IKKT matrix model. And the second one is just apply matrix realization without weak rotation. So you may think that would not be healthy, but I would say it's possible because we consider the shift action. So in the Polyakov type action, we have the worldsheet metric, but in the shift type action, we have worldsheet coordinates as just parameters. Since these are just parameters, we can consider it as a compact manifold with punctures. So yeah, by considering punctures, we may think the worldsheet as the compact manifold. So by considering such kind of compact worldsheet with punctures, we just apply the matrix realization to the worldsheet theory to obtain the matrix model. That would be yeah, there wouldn't be a problem because the fuzzy sphere doesn't care about small punctures. So as long as we matrix regularize theory, these kind of punctures wouldn't harm the theory. Okay, so in order to get the matrix regularized theory, we fix the fermionic gauge. In this way, we are considering type 2 theory. So we equate θ1 and θ2 after we rotate θ2. Then we obtain this gauge fixed shift action. Now, by matrix realization, applying this standard procedure, we get the matrix model. By using the first matrix realization after the weak rotation, we get the Euclidean IKKT matrix model. If we fix EG equals to 1 after the weak rotation. And the second procedure, without weak rotation, it gives something different. If we don't fix EG, and we matrix regularize EG as well to -y, so this second one is what we obtain if we apply this second method without weak rotation. And this model is called something like NPI type IKKT matrix model by the researchers at Niels Bohr Institute at the time. So yeah, this is what we get. And actually, this NPI type matrix model in the Minkowskian signature has a good feature in it.
NBA stands for.
It's a double meaning, actually. These guys are from Niels Bohr Institute, and they mean non-abelian Born-Eifeld action. Yeah. But at the time, they proposed this model in the Euclidean signature. But actually, we are considering this type of action in the Minkowskian signature. Okay, so unlike the Euclidean IKKT matrix model, it can contain some causality property. So by causality property, I mean that, well, by integrating out the matrix EG, which is Y here, we can do this because this is Isaacson-Zuber type matrix integral, so we can do that. And this is the result. Now looking at this factor, the structure is just the same as the structure we have seen in perturbative string theory. And okay, so yeah, here M is x mu squared, and small m is just the eigenvalues of M. Now, looking at this, if at least one eigenvalue small m is negative, then this cancels. And it's determinant, so yeah, it's 0 if at least one eigenvalue of m is negative. So this is a similar cancellation in vector string theory, and we call it causality property in the matrix model. Of course, without interpretation of matrices, we cannot say something meaningful about causality, but I think this might give some hint to the causality or interpretation of matrices. Okay, so this part will be explained by Jun Nishimura and Joe Gens. So I would like to skip this part. Okay.
That are those two models, if you are the MBI models, is it equivalent to the IKKT? Is it the Lorentzian?
It's Lorentzian.
Lorentzian version of the IKKT?
Yes, it is.
Think of it.
Yeah, it's defined in this way: expansion of I, S, and MBI, and X mu nu are contracted by eta mu. So it's Minkowski, totally Minkowski. Sorry, did I answer your question?
I mean, so is it the Lorentzian version of the IKKT, or is it something really different?
It's sort of different. It's the Lorentzian version of NBI type Euclidean matrix model.
So it is not Euclidean itself. There is an I.
This is Minkowski.
Yeah, it is.
So there is a Euclidean version of NBI type.
So there is an Euclidean version of this one,
right,
which is different from the IKKT, Euclidean IKKT.
Well, not equivalent. No.
Sorry.
Is
it classically equivalent to Lorentzian IKKT or?
Classically, no. No. Classically, if you integrate out y, then you will get square root of x mu nu squared, the commutator of x mu nu squared. So it's different from the IKKT. Okay, so time is run up. I'd like to summarize my talk. So I've explained the equivalence between the Minkowskian and Euclidean in the quantum mechanical sense, and we've discussed Polyakov, Schultz, and Navigoto type formations, and we saw the equivalence of them of the formations quantum mechanically. And we also saw that causality is inside the particle string theory, and we can inherit the causality into the matrix model as well. Okay, so yeah, so this partially answers to how we define the IKKT matrix model in path-into formalism. And as future work, well, the motivation of this work is actually I'd like to find exact relationship between perturbative string theory and matrix degrees of freedom. And it was discussed by Fukuma, Kawai, Kitazawa, Tsuchiya, and also, Harold's string states also has tries to find the exact relationship between them. So yeah, I'd like to work on this problem in a different point of view. So yeah, one way to consider about it is using vertex separators. So as we have seen, the matrix model has some relationship with the perturbative string theory in the way of matrix realization. So maybe through that course of discussion, we can find some relationship between them. So yeah, that's one way to proceed with this work. And another one is Maston. As Sean explained, there is a polarized IKKT matrix model, and it provides omega, the parameter omega in the matrix model. So it's possible that some double skin limit of the polarized IKKT matrix model gives some something like what we have seen in SQL one matrix model was kind of seen as a double scale limit. So this is another thing I'm thinking about. So okay, so yeah, let me finish. Thank you very much.